Hi, I'm Bill Weinman, and welcome to Python 3 Essential Training. The goal of this course is to provide you with the basic knowledge you'll need to write effective Python scripts. We'll start with an introduction to the basic syntax of the Python language. I'll explain how types and values are related to objects in Python, how to use Python's control statements, conditionals, loops, and functions. I'll cover Python's unique object model and how it relates to just about everything in the language. I'll describe Python's generators and decorators, and finally, I'll show you Python's simple and powerful module system along with an example of a real Python web application. A thorough understanding of Python will help you write more efficient and effective scripts, so let's get started with Python 3 Essential Training. The exercise files for this course are included with your basic membership. Copy the exercise files to a location where you can find them on your system. I've copied mine to the desktop on this system. Wherever you put them, just make sure that you can find them. The exercise files for this course are laid out by chapter, where each chapter has a folder, and the files for that chapter are contained within the associated folder. Most of the exercise files are simple Python scripts. To use one of these files, first make a working copy. I'll select the file and I'll copy and paste. On a Mac, that's Command-C and Command-V. On a PC, that would be Control-C and Control-V. And then I'll rename my copy to something that makes sense, and then open my working copy either in my editor or in my development environment. Here I'm using Komodo Edit, and I simply double-click on the file, and there it opens, and I can run it, and there's my result. When you're done working with the copy, you close it in your editor, and you may delete it if you like, or you may keep it for further study and experimentation. The exercise files are here to make your learning experience easier and more powerful. Take your time, experiment a lot, and happy learning. Python is a modern object-oriented scripting language. Python was developed in the late 1980s by Dutch research programmer Guido van Rossum. Guido wrote the first Python interpreter over his Christmas holiday in 1989. He chose the name Python as a reference to Monty Python's Flying Circus. Guido remains Python's principal author to this day, and the Python community affectionately refers to him as BDFL, Benevolent Dictator for Life. There's a core philosophy behind the Python language which includes the following statements. Beautiful is better than ugly. It's always a good idea to make your code elegant and readable. Explicit is better than implicit. Don't make your readers guess what your code does. Make it obvious. Simple is better than complex. If you can make it simple, do. Complex is better than complicated. If complexity is necessary, don't complicate it. Readability counts. As a casual reader with a good understanding of the Python language, you should be able to understand the code with a minimal amount of effort. For the complete list, simply type import this into any Python interpreter. Python 3 is very close to Guido's ideal vision for Python. Code written for Python 2 must be ported for use with Python 3. All data types, including functions and classes, are now built on Python's object model. In Python 2, print was a keyword, and it didn't require parentheses. In Python 3, it is a function, and it does require parentheses. Python 2 had separate types for integers and long integers. Now there is just one integer type. Python 2 had separate types of strings for Unicode, ASCII, and 8-bit data. All text is now Unicode, and there's a separate 8-bit data type. This course teaches Python 3. There's a lot of legacy code written for Python 2, and it may be important to maintain it for a while. As I record this course, Python 3 has been around almost 10 years, and the amount of legacy code is diminishing. I strongly recommend that you write new code using Python 3 exclusively. Python is a rich language, and it would be impossible for me to cover all of it in the time allotted for this course. The online documentation is both accessible and exhaustive. I recommend you become familiar with it. Python is a very powerful and versatile programming language. It's supported on virtually all common operating systems, and it's easy to learn and to support. In the rest of this course, I'll show you the essentials of Python so you may develop quick and easy solutions to common problems, as well as larger, more complex interactive systems. To follow along with the exercises on a Mac, you'll need the latest version of Python 3, and I recommend the free version of an editor called PyCharm from JetBrains. Keep in mind that your screen will look different than my screen in the lesson videos. That's because I recorded those lessons earlier using a different editor called Komodo Edit. When this course was originally recorded, I recommended using Komodo Edit on the Mac. Unfortunately, Komodo Edit no longer works properly in the latest version of Mac OS, and after waiting for several months, it's not fixed, and the developer cannot say when it will be fixed. So I'm suggesting you use PyCharm instead of Komodo Edit, and I'm recording this video to show you how to install it. So this lesson will show you how to install Python 3 and PyCharm, and just keep in mind the screens in the lessons are using a different editor, so they will look different. You can download Python from python.org/downloads. And I've already done that, and it's on my desktop. And you can download PyCharm from this page here at jetbrains.com/pycharm/download. You'll notice there's two editions of the PyCharm editor. One of them is the professional edition, which costs money, starting at $200 per year as a subscription. I'm sure that's great if you're developing projects for clients, but for our purposes, you probably don't need it. So for the exercises in this course, I'm using the free Community Edition. You'll notice it says Community Edition there for pure Python development, and you can download it with that download button. Not this one. That'll get you the professional thing. You want this one here. And I've already downloaded both of these things to my desktop, so I'm going to go ahead and quit out of Chrome using Command Q on my Mac keyboard here. And you notice I have my exercise files on my desktop. I have the Python installer and I have the PyCharm installer. And we're going to start with the Python installer. We want Python installed before we go to PyCharm. And so I'll double click on the Python installer. And we're just going to press the buttons here. I'm just going to presume that you either read or don't read your license documents. I don't think anybody actually reads them. So we're just going to go ahead and agree to this and press install. I'll type my password. This actually goes pretty quickly. And you notice that it opens a little Finder window here, and underneath that Finder window is that installer, and it's still working. So we want to just let it finish, and then we can press the close button. Now, it gives us this Finder window because there's a number of things in here, including some documentation and such. But there's also this wonderful little app called IDLE, I-D-L-E. It's a little mini integrated development environment. We get these dialogues all the time on the latest versions of Mac OS, so I can just say okay. And you notice that it's just a little shell with Python in it. And the reason I'm bringing this up, first of all, it validates that our version is 3.9.1, and so that's good. Yours will say that version or maybe a later version. And I can actually type Python instructions here. I can say print, and in parentheses, I can say hello. And hello is in quotes. I do not need a semicolon. I'm too used to programming in C. And then I just press enter, and it says hello there. And so you get this perfectly functional little development environment, and it's perfectly usable. You can even use that for this course if you want to. I think PyCharm's a lot more friendly, but it's there for you to use. So I'm going to quit out of that, and I'm going to quit out of this Finder window here using Command W on my Mac keyboard. And before we install PyCharm, I want to validate a couple of things. So I'm going to come down here to my dock, and I'm going to open my terminal. And in here, I'm just going to type Python 3 and a dash and a capital V, not a lowercase v. Lowercase v will do something entirely different. You want the capital V. And when I press enter here, you see it says Python 3.9.1. And that's the version that I want. And if I say user/usr/local/bin for bin /Python 3 dash capital V, you notice I get the same thing, 3.9.1. Now, it's worth noting here that you may get a message about installing developer tools if you don't have Xcode already installed on your Mac. And if you get that message, just go ahead and install the developer tools. That's going to be necessary for you in order to run Python. All right, so you want to just make a note of this. This is the path to Python, and we're going to need that later. So it's USR local bin Python 3. I'm going to go ahead and quit out of my terminal now, and I'm going to install PyCharm. So I'll double click on the installer. This is one of those ones where you just drag it into the applications folder. And so I'll just drag this into the applications folder, and I want to wait for it to copy. And I'm going to do something a little different here. You can open a separate Finder window and go to applications, but I'm just going to double click on applications here because that works just as well. And I'm going to scroll down here until I see PyCharm, and there it is. I'm just going to drag that to my dock. So I'm going to drop it in right there. And now I can close this Finder window, and I want to eject this because this is a DMG. So I'm going to control click or right click and select eject, and that'll eject that DMG, which is actually mounted like a drive. All right, now we can come down here to our dock, and I can click on PyCharm. And again, we're going to get these dialogues here. So I'm going to say we want to go ahead and open this. We know that we just downloaded it from the JetBrains website. So I'm going to go ahead and open it. And I'm not interested in notifications from my editor. If you are, you can allow them, but I'm just going to say don't allow up there. And I'm going to confirm that I have read and accepted the terms of usage. And we all know how I feel about that by this point. Data sharing, I'm okay with it. You can say yes or no. It doesn't really affect how anything works. And now we get welcome to PyCharm. Now, there's a few things we need to do here before we can start using it. First of all, I'm going to come down here to customize, and I'm going to select the Mac OS Lite. You don't need to do this, but for the purposes of these videos, this is easier to see on a video. And I'm also going to increase the size of my fonts because, again, for the purposes of these videos, which are on a relatively small workspace, it makes it easier for you to see as I'm teaching. Again, you don't need to do those things. And then I'm going to come back over here to projects, and I'm not going to start a new project. I'm simply going to open my exercise files folder. And so we'll select open here. And then on my desktop, my exercise files folder, and I'm just going to open that. And that will load this into a PyCharm window. You notice all my fonts are big now, just like I wanted. We'll get a tip of the day. We're going to get all these dialogues about opening folders. I'm just going to say, okay. It's never going to need those folders, but maybe it will. Who knows? You notice that it's configuring things down here, and we're going to change that in a minute. You get your tip of the day. You might like them, and they might be useful to you if you want to use PyCharm more than just in this course. I think it's a great little editor. I've switched to it myself. But for my purposes for right now, I'm going to say don't show tips because I don't want it interrupting our lessons. So I'm going to say close. Now we're almost there. We got a couple more things we have to configure before we can move on. We need to come up here to PyCharm and preferences, or you can press Command, which is common on all kinds of Mac applications. And there's all kinds of things that you can configure in here, but I'm going to come right down here to our project. It says project exercise files, and I'm going to open up that little disclosure triangle, and I'm going to select interpreter, because we actually want to make sure that we're using our interpreter. And you remember we have USR local bin Python 3, and here it's actually selected Python 3.9. So this is what you want it to say. And again, you might have a later version. You might be watching this sometime in the distant future when it's 3.10 instead of 3.9, and all of that is fine. You just want to make sure that that's the interpreter that is selected here. So Python, it went and configured, and it found the right interpreter. Your Mac actually comes with a couple of older versions of Python, including one from the Python 2 tree and another earlier one from the Python 3 tree. And so this is the very latest Python, and this is the one that we want to use. So I'm going to say OK. And now at this point, I'm going to go ahead and I'm going to open one of these files. Here, you see, we're getting there. I'm going to double click on hello-version.py in the chapter 1 folder, and you'll get this file. And you notice that my cursor is blinking. That means I'm in this file. So this file has the focus. And now I'm going to press Control-Shift-R. And when I press Control-Shift-R, I get this terminal window down here. I'm just going to maximize a little bit for a little extra space. And I get this wonderful little terminal window down here where it has run my Python script. And see, it says this is Python version, and it has this placeholder for the Python version. And it prints out down here, this is Python version 3.9.1, which is exactly what we want to see. So this validates that our development environment is now working. Now let's look at a little bit about how we use this development environment, because now we have several windows open and we want to know how to navigate them. We want to know how to do the things that we're going to need to do in order to follow along with the exercises. Now, the terminal at the bottom, there's a couple of ways you can close this. One is with just Command W, like you normally would close a window. As long as it has the focus, you can do that. I'm going to go ahead and run it again with Control-Shift-R, and we got it there again. Another thing you can do, and if you're familiar with Unix, you'll already know this, is you can press Control-D, and that closes any terminal window. That's the Unix command for that. And of course, we know that Macs are running Unix. All this pretty Windows stuff is on top of BSD Unix. So the same thing is true here. We can close this window also. You can close it with pressing that little X, or you can just say Command W, which is normal on a Mac for closing a window. That's just the normal Mac closing a window thing. You'll also want to know how to make working copies, because you may want to make a working copy so that you can edit the file and experiment with the language. So if you hold down your Option key and drag it, and again, this is very common Mac thing here, I can just drag it to another spot in that folder and it'll say it wants to copy the file. So that's Option and drag. And then I can give it a new name. I can say working. That's what I like to name my working copies. And I can just press the Enter key, and it's made a copy, and there it is, and it's opened it in the editor. And again, I can run it with Control-Shift-R, and now it's running hello version working.py. When you rename it, you want to make sure you don't change the file extension. .py is necessary. All right, so I'm just going to close that window. And I'm going to close that window. Now, if I happen to open two files, you'll notice I can open two of these. You notice it opens them in tabs. And you'll also notice if I run two different things, so let's see, I'm going to open Fibonacci down here. It's in a different folder. If I run something in a different folder and I say Control-Shift-R, I get this terminal down here. But if I then go and also run this one from a different folder, Control-Shift-R with this one open, you'll notice I get two tabs down here. So it's very possible to end up with a whole lot of tabs open, and just don't worry about that. They're easy to close. Command W, Command W, Command W, Command W, Command W, and all of those windows are closed. All right. There's one more thing I want you to notice. If I open this Fibonacci.py again, you'll notice that I get some warnings. You see over here, the little warning thing, 5 warnings. And I'm going to click on the Problems tab, and it lists these 5 warnings. You notice that all of them say PEP 8, PEP 8, PEP 8. Okay, so there's a little story here. PEP stands for Python Enhancement Proposals. These are like RFCs, requests for comment. They're not standards, they're proposals. And PEP 8 is a style guide. And the purpose of PEP 8 is to help you write code consistently so it's readable. And PEP 8 is about 3 miles long, full of all kinds of different rules that you can follow to make your code nice and consistent. And I have not followed PEP 8 in any of these files. And the reason for that is that it didn't really matter to me. I code very carefully with very careful standards of my own style that I've been using for decades in many different languages. Things like putting spaces around equal signs. I like spaces around equal signs. PEP 8 says not to do that. So I want you to ignore these warnings. or you can reformat them and learn about PEP 8 if that's what you want to do. But what I am going to do is I'm going to come up here into my preferences again, and I'm going to come down here to, I'm not seeing it there. Maybe I need to close all this stuff for that to happen. I'm going to come up here and search for it. Inspections. There it is. It's in the editor. It's under editor. Inspections. There we go. And under inspections, we look for Python. And then I'm going to scroll down here. You notice there's all kinds of inspections that it does. These are for all the warnings that it has. And I'm going to find the ones that say PEP 8, and I'm going to turn them off. And that's all I'm doing. That doesn't affect how the code runs. It doesn't affect how you learn to program in Python. I never even knew I was violating PEP 8 until I started using PyCharm, which actually checks and gives me all these warnings. So now I can open Fibonacci and the warnings will go away. They should go away. I just turned that off. Oh, I didn't say okay. I have to say okay. Haha. There we go. And now those warnings go away. All right. So PyCharm is now installed and it's working with Python 3. Don't forget, your screen is going to look different than my screen in the lessons videos. And that's because I recorded those lessons using a different editor that just no longer works under the latest Mac OS. So I'm going to go ahead and I'm going to close this and I'm going to close that. And PyCharm is now installed and working with Python 3, and you're ready to continue this course beginning in the next chapter. To follow along with the exercises in Windows, you'll need the latest version of Python 3, and I recommend the free version of ActiveState's Komodo editor. Here's how to install these components on Windows. Here in my browser, I've opened python.org/downloads. And this is where you download Python. You'll notice there's two buttons, one for Python 3 and one for Python 2. You'll want to download Python 3 and not Python 2. Python 2 is for legacy systems and legacy development. This course is going to teach you Python 3, so you'll need Python 3. So you'll press this download Python 3 button, and I've already done this and I've downloaded it to my desktop. So I'm just going to double click on that and press the Install Now and accept the security dialog and wait for the installation to complete. Once the setup is complete, you simply press the Close button and Python is now installed. Now I'm going to open my browser back up. I've opened activestate.com/Komodo edit, and this is where we'll download Komodo edit. You notice over here there's two download buttons, one for Komodo IDE and Komodo Edit. Komodo IDE is the pay-for-it version, which costs about $300 to $400 for personal use. Komodo Edit is the free version, and that's what we're going to use. If you'd like to see the differences, there's an exhaustive list of all the features that are available in the pay version that are not available in the free version, and if any of those features are worth the money to you, then feel free to use the pay version. I'm going to be using the free version, Komodo Edit, and if you want to follow along and have your screen look just like mine, you'll probably want to use that as well. Just press the Download Komodo Edit button and it'll bring you to this separate download page where you can press the big Download Komodo Edit button. I've already done that, and I've saved the installer here on my desktop. I'll double click on it and we'll go ahead and install it. So I press Next and accept the license terms, which I have not read, and press Next and Next again and install. Accept the security dialog and wait for the installation to complete. Now, if you want to read the user guide, you can leave that checked. I'm going to uncheck it and press Finish. I'm leaving Launch Komodo checked so that it'll go ahead and launch, and I press Finish and wait for it to launch. The first time you run Komodo Edit, you get this little configuration dialog. For my purposes, I'm going to select a different color scheme. You can use the default or use whichever one you want. I'm going to select this one that says Redmond. It's a little higher contrast for the purposes of this demonstration video. And I'll go ahead and press Next. And 4 spaces of indentation is perfect for me. You can change it if you like. Your screen, if you want your screen to look just like mine, you'll leave it at 4. I never like tabs, and I'm glad that's unchecked by default. I'll go ahead and press next and press finish, and it'll launch the Komodo editor. And I'm going to go ahead and maximize this. So I've modified this version to make the interface more readable for the purposes of this video environment. You should configure your copy to your own preferences, and you can do that by pressing on the Preferences button here, and you can select your interface colors, and you can even come down here to Color Scheme, and you can open the Color Scheme editor and customize it to your heart's content. For now, what we need to do for the purposes of using this environment with Python, you'll need to make sure that the Komodo editor is configured to use Unicode encoding for all the files we're going to use. So we set our default encoding to UTF-8, and if that is not already the default, you want to select that. And then, so this is an internationalization, if I didn't say that. You select internationalization over here on the left, and now I'm going to select the Python language. I need to do this for both Python and Python 3. So we'll start with Python. You notice it says ASCII. We want to change that to UTF-8, and Python 3 also to UTF-8. Python 3 is fully Unicode compliant, and this makes Komodo work with Unicode characters. So this is very important. Some of our exercises will not work correctly if we don't do this. So now I'm going to press OK, and now we can test everything and make sure that it all works. So I'm going to come up here to this little gear icon in the left-hand pane, and I'm going to open directory and go to my desktop and select the exercise files. I don't want to open it, just select it and press select folder. Now you see my exercise files all show up here in the left. I can move this projects thing out of the way because I don't need it. And there's one final bit of configuration that we need to do. We need to create a run command to run the Python scripts. You'll remember that this is Komodo Edit. It's not Komodo IDE, so it does not have some of the IDE functionality. We can create that very easily by creating a small run script. So I'm going to open the right pane by pressing this button here, and I'm just going to right-click in the empty space here, select Add, and Add Command, New Command, that one there. Now, under Command, I simply type py, which is a special command that'll run the Python interpreter, and press this little button here and select the capital F for file path, like that. And that actually needs to be in quotes. So I'm going to put quote marks around it. And it's very important that all of the characters are exactly like this. Lowercase py, space, quotation mark, %, F, and a close quotation mark. And that will run the Python scripts. So I'm going to select this here. This is actually for the title. It's not labeled there, but I'm going to type in here run and -R, because that'll remind me that I have to press the key binding for R. So we're going to leave that for a moment. We'll do the key binding in a moment. We're going to go to Advanced Options, and it's important that Start In, we have our current directory. So again, I'm pressing this little arrow over here, and the %D for directory path of file. And then I come over here to key binding, and there's no current sequence. We're going to add a key sequence that will run this script. So I'm going to press Control and Shift and hold both of those down and press the R key. So that's Control Shift R, which should show up just like that in the dialog box, and press the Add button. If you don't press the Add button, this doesn't get saved. So we have our key sequence there. It says Control Shift R. We have %D here, and we have our run command here. Everything is okay. I'm going to press OK, and there's our run command. But we don't need that because we can use the hotkey there for it. So I'm just going to close that right pane again. We'll come over here and open up a script. This hello version.py, press Control, Shift, and R, and it runs the Python script here in our development environment. So this is perfect. This is exactly what we need. Here's the script in the nice big letters that I've configured this so that you can see it clearly on your screen. Here's the script, and here's the output when it runs it. It says this is Python version 3.6.3. So now everything is working. Python is working. Our Komodo editor is working, and it's configured to find our exercise files. We have the run command working and the customized key press to run it. So all I have to do here is load the script up and Shift Control R, and it runs it. So now I'll just close my script. So we're all set up for the first lesson, and that's all there is to it. Your computer is now set up to run Python scripts in Komodo Edit. Python does not look like a lot of other languages. It doesn't use braces or semicolons. Line endings and indentation are meaningful. And in Python, everything is an object. Before we delve into the details of language features, it can be useful to see how all the pieces fit together. This chapter provides that bird's eye view of the language as a whole. We'll use examples to describe different elements of Python syntax without getting into much detail about how each feature works. The idea is for you to become familiar with the syntax of the language so that you may better learn its features later. Don't worry about the details for now. We'll get into a lot of detail in the later chapters. Think of this chapter as the cover picture for a puzzle, so you'll have a vision of what the whole puzzle looks like as you gather all the pieces. The Hello World program is a traditional first step in learning a new language, but it's actually more than that. Here in Komodo, I've opened a working copy of hello.py from Chapter 2 of the exercise files. The purpose of Hello World is to validate your development environment. Whenever you set up a new development environment, it's a good idea to use a simple, minimal, and functional program to confirm that your development cycle functions as you expect. And that's what Hello World is for. So here we have that simple, minimal, functional program in Python, and it basically has one line of code, this one here. It says print, and it's called the print function with hello world string. And when I run it, you see the output says hello world. So that validates that our tool chain is functioning. My interpreter is working and the command output is working. So if I were to change this, let's say I add a new line of code, print something entirely different, and I save that and run it. Now we have two lines of output in our output at the bottom in the command output because I added a second print function, a second print call. So I delete that and I run it again, save and run, and it still works. So this validates that our entire tool chain is working. We can write, we can update, we can save, we can run Python scripts in this development environment. And whenever you change your environment, it's always a good idea to test it again with a simple hello world script. So now I will close this and delete my working copy. And now I'm ready for the next lesson. A Python script is simple, but it's somewhat different from other scripting languages. Let's take a look at the different parts of a Python script. Here in Komodo, I've opened a working copy of hello version.py from Chapter 2 of the exercise files. And up here at the top, you'll see the first two lines are comments. So comments are introduced by the hash mark or the pound sign. And the first comment is a special case of a comment. It's called a shebang line, or sometimes hash bang. The shebang line is a common pattern for Unix-based systems. It allows a script to be invoked from the command line. There are two parts to the shebang line. The hash mark and the exclamation sign must be the first two characters on the first line of the file. These marks together form the shebang. An exclamation mark is sometimes called a bang, so hash plus bang is where the word shebang comes from. There must be no lines before this line and no spaces before these first two characters. Essentially, these two characters must be the first two bytes in the file. After the shebang is the path to the executable that will run your script along with any optional arguments. In this case, we're using the Unix env command, env, to find the path to the Python interpreter. This is a common usage. Alternately, We could use the absolute path to the Python interpreter. I didn't use this method because these example scripts must operate on different installations, and I cannot predict the path of the Python interpreter on different systems. For our purposes, I use the env command in the examples for this course. If you're on one of those systems that is not based on Unix, like perhaps Windows, this line, because it starts with the comment character, will be completely ignored. On Macs, it is actually functional because Macs are based on BSD Unix. Following the comments, the first line in the script is an import statement. This tells the Python interpreter to import a module from the library. The module may contain any combination of classes, functions, or other Python objects. In this case, it's importing the platform module, which is used to display the Python version when we run the script. There are standard library modules, or you may define your own. A Python script may have multiple import statements, or you may specify multiple modules in one import statement. After the import statements, you find the rest of the script. In this case, it's this one line, which is a call to the print function. In versions of Python before version 3, print was a statement. In Python 3, print is now a function, and it always requires parentheses. Inside the parentheses is a string. And you notice that because everything is an object in Python, we're actually calling a function on this string object, the format function. And that formats the text inside these curly braces. We'll get into more detail on the print function later in this course and also on string objects. So when I run this, and I'm pressing Shift-Command-R here on my Mac or Control-Shift-R on a PC, and there we have the output, and you notice it says this is Python version, and it gives the version number, which we're getting from the platform module. So there's a common variation that I'd like to show you. I'm going to switch to this other tab here. Here I have a working copy of hello main.py from chapter 2 of the exercise files. This is functionally the same as the other script. It calls this print function with the format and the Python version. You notice that the print function is actually called from inside a message function, and message is called from main, and then we call main down here at the bottom in this conditional statement. This is actually a very common pattern in Python. By having this conditional statement at the bottom that calls main, it actually forces the interpreter to read the entire script before it executes any of the code. This allows a more procedural style of programming, and it's because Python requires that a function is defined before it's called. Again, we'll get into a lot more detail about this later, but you'll notice that when I run this, it gives us exactly the same output. So I've described the general anatomy of a Python script. It's pretty simple, and we'll get into more detail about each of these parts later in this course. The distinction between statements and expressions is a bit different in every computer language. Generally speaking, a statement is a unit of execution, and an expression is a unit of evaluation. In a scripting language like Python, these definitions require further explanation. In Python, an expression is any combination of literals, identifiers, and operators. Generally, this means anything that returns a value is an expression. This is an assignment. It assigns a value to a variable. This is an operation. You notice it has an operator, the multiplication symbol, and so it returns the result of that operation, the result of that multiplication. This is an aggregate value. In this case, it's a tuple. This is a simple value. This is a built-in constant value, and this is a function call. All function calls return a value in Python, even if the value is none, which is the absence of value. A statement is a line of code. It may be an expression, or it may be something like the import statement or a break or a continue. Here in Komodo, I've opened a working copy of statements.py from chapter 2 of the exercise files. We'll go ahead and run this so you can see what it does. It simply prints out this is Python version and the version number. In Python, a statement is a line of code. It does not require a semicolon at the end of the line. And so this import statement is a statement. This assignment, even though it's also an expression, is a statement because it's a line of code by itself. And then this print function, of course, is also a statement, and it's also an expression because even though we're not using the returned value from the function call, it still does return a value. Now, in most cases, you'll see one statement per line. So if I add another line of code here and save that and run it, you can see in the output we now have 2 print results. And so one statement per line is normally how you will see Python code. Python does not require a semicolon at the end of the line, although you may put more than one statement on a line. If I put a semicolon here and put that other print statement on the same line, I'll run it, you see we get the same result. This is possible and it's extremely rare. You almost never see this in Python. You'll far more often see one statement per line like this. So statements and expressions are simple concepts in Python, and understanding their distinctions will help you write code that is clear and easy to understand. Unlike most other modern scripting languages, whitespace is significant in Python. Here in Komodo, I've opened a working copy of hello main.py from chapter 2 of the exercise files. In Python, a block is delimited by indentation. There's no brackets or parentheses to match up, just indents. And so these two functions, main and message, they have blocks which are associated with them, and that's the code that comprises the body of the function. And you notice that they're indented under the definition of the function declaration, the function definition. And so the main function has a function call to the message function, and the message function has a function call to the print function. And you can tell that these are associated because of their indentation. Now, if I take this message function, well, let's go ahead and run this, and you can see that it prints, this is Python version and the version number. And so if I take this and I just add another print, let's say print line 2, and I save that and run it, you see now we have a line 2 in our output. And I can do this again and make that one line 3 and save that and run it, and now we have 3 lines of output. And we can tell these are all part of this same function because they're indented. If I were to unindent one of these lines and save that and run it, now that line 3 will come first because it's outside of all of the functions and it's getting executed before main is ever called down there on line 14. And if I re-indent it and save it, now it's part of that function again because it's indented with the rest of the block. So a block is indicated by the common indentation. So these are all indented exactly the same, so they're all part of exactly the same block. If I wanted to, I could say if true and make this part of a separate block, and we'll give it an else, print not in the block, not in the if, not true. We'll just say not true. If I run this, we get the line 3. And if I say false and save that and run it, now we get the not true. And so these are part of separate blocks. That whole if is part of that other block, but these are indented in another level, and so they're part of a different block. Comments in Python are introduced by a pound sign. So if I come here and say this is a comment, of course, that's not code and it doesn't run. So when I run this, we still get the same result. A comment ends at the end of the line. And so there's nothing like a multi-line comment in Python. If you want to make a multi-line comment, you have to do it something like this. So in most languages, white space is mostly ignored. In Python, it's meaningful, and you must be conscious of formatting as you write your code. And in Python, comments are introduced by the pound sign or the hash sign, and they end at the end of the line. Again, that end of the line is significant in Python. The Python print function is simple and powerful, and it's probably a bit different than what you're used to in other languages. Here in Komodo, I've opened a working copy of hello.py from chapter 2 of the exercise files. And you'll notice that down here on line 4, I have a print function with a literal string, which says hello world. And so if I save and run this, you see the output says hello world. Now, if I want to print a variable value in the string, I'll use the format method, which is actually a method of the string object. And so I put a placeholder in here with a pair of curly braces, and I say dot format, and I'll put a value up here. I'll make a variable, x equals 42, and I put that x in the format method. And when I save and run, you see now we get a 42 down there in our output. The format method is very powerful and very flexible, and we'll cover it in detail later in the course. But for now, you know enough to use it in many, many cases. It's worth noting that this is not a function or a method of the print function. This is a method of the string object itself. And so I can take this whole string object, including the format call, and put it on a separate line and say s equals and print s, and you see we'll get exactly the same result when I save and run this. So for now, I'm going to put this back the way that we had it. And save and run. You can see it still works. Now, earlier versions of Python, like Python 2, which if you're familiar with Python 2 or if you see legacy code, you'll see a lot of Python 2. It works very differently because print is not a function and strings are not objects. And so instead, it works more like C, but not entirely. So I would say %d here and close the string. And I would use a % here and then the variable. And so that would replace the placeholder %d, which that placeholder is now specifically for an integer value. That d means d for an integer value, just like it does in the C language. And so when I save this and run this, you see we get exactly the same result. Now this usage, this is used in legacy code that uses Python 2. It's deprecated and it will be removed from future versions of Python. So instead, you're going to want to always use the format method when you're using Python 3. And so I'll put the X there, and I need to replace this with the placeholder. And because my editor is trying to help me, it did that. And so we save and run, and we have now that same result. Now, beginning with Python 3.6, this is not in all versions of Python 3, just beginning with 3.6 and later. And what we have here is 3.6.3, if I remember correctly. We can take all this format stuff out and not call the method like that, and instead use what's called an F string. So I put the letter F in front of the string, and then I simply put the X variable inside of the curly braces, and when we save and run, we see that that works exactly the same. So F stands for format, and the F strings are actually implemented by calling the format method. So it has all the relevant functionality from format. And again, we'll cover this in a lot of detail later in the course. But for now, this is how interpolation and formatting of strings works in Python 3. Python differs from many languages in how blocks are delimited. Python does not use brackets or any special characters for blocks. Instead, it uses indentation. Here in Komodo, I've opened a working copy of blocks.py from chapter 2 of the exercise files. And you'll notice that down here on line 7, we have a conditional statement if x is less than y. And indented below that is this print statement. So that indent means that it's a block and it's associated with the control above it, in this case the if statement. And so if I save and run this, you'll see that we get that result from the print. And if I put another print down here and save and run, you see we get both of them. But if the condition is not true, if I change that condition to if x is greater than y and save and run, you see now we only get the something else. And I can put several other lines of code in here and save and run, and none of those are printed unless the condition is found to be true. And if I save and run, now we get all of that. So that is a block. Now, if, for example, this last line, and let me change this again to something that's not true, and take this last line and just unindent it. And now you see it's no longer part of that block. And if I save and run, that line 4 is still executed. If I indent it differently, just part way, you'll notice I've got an error up here at the top because this editor is checking syntax. And if I try to run this, you see that I get an error that says unindent does not match any outer level indentation level. And that's because at this level, there's no block that matches this level. The outer block is at the level of 0 indent, and the block under the if is indented at 4 characters of indent. And there's no block that it can match with it. The parser in the interpreter has no way of knowing what I meant by this. It either needs to be indented all the way with the other ones or not at all, or at the level of the if itself. And so again, I'll save and run, and we see that that line 4 is now part of that same block. So blocks in Python are indented, and that indentation is how the block is defined. They all have to be indented at the same level. There can be white space in between them. As long as they're all indented at the same level, they'll be considered part of the same block. Now, it's worth noting that blocks do not define the scope of variables in Python. And so if I come up here and I make this true again and save and run, and you see that that block is now being executed, and I'll define another variable in here. I'll say z equals 112. And down here in my print statement, outside of the block, I'm going to say z is, and when I save and run this, you'll see that I get my result, z is 112. And that's because even though the variable is defined inside of that block, its scope is still the same as the code outside of it. Blocks do not define scope in Python. Functions, objects, and modules do define scope in Python, and you'll see examples of this later in this course. But as we're talking about blocks, it's important to understand that the block itself is not what defines the scope in Python. So blocks in Python are indicated by indentation, and you'll see many more examples of this as you proceed throughout this course. Conditional statements in Python work in familiar ways. Here in Komodo, I've opened a working copy of blocks.py from chapter 2 of the exercise files. And down here on line 7, you'll see a conditional statement. It has the keyword if, and it has the condition, x is less than y. If the condition evaluates to true, this print statement will print, and we have that colon there to indicate the end of the condition. And the print statement is indented under the conditional statement so that it is an associated block. And if I save and run this, you see we get the result, the print statement is printed. Now there is a variant here which is not often used in Python, but it is available to put the print statement on the same line as the condition after the colon. And in this case, you don't get a block, you only get one line of code. And in many cases, that's fine. And of course, you save and run this, you get exactly the same result. In practice, it's frowned upon to put it on the same line as it is in many languages. And even though it works, you'll see most of the time it's done this way, and this way is considered the Python way, with it on a separate line and indented. Now I can also have an else statement and say else print do something else. And if we change the condition to a greater than, then that'll be false and we'll get the else. And if I save and run, you see our result is do something else. We can also have an elif. I'm going to change this to say greater than because that is now that condition. And I can say elif and a colon, and I can copy this and say less than. And if I save and run, oh, I didn't give a condition. I need my condition. There we go. And if I save and run, we now get the elif, the less than, printed. So elif is like else if, and it requires a condition. It's just like if, only it happens in the case where the preceding if is not evaluated to true. In fact, you can have more of them. You can have an elif equals, and if we make these two values equal, then save and run, and now the equals is executed. And so you can have as many elifs as you want to In fact, you can do something like this. If x is equal to 5, print do 5 stuff, and elif 6, etc. And so if I save and run this, we'll get do 42 stuff. Or if I change x to 112, then we get do that other thing. So Python doesn't have a switch or a case statement, and it can easily be argued that it does not need one, which is why it doesn't have one, because you can do exactly the same thing with a string of elifs. And this is typically how that's done. So conditionals in Python work as expected with if, else, and elif, and it doesn't have a switch or case statement, and indeed it can be argued that it doesn't need one. We'll discuss conditional operators in more detail later in the course. Python provides two basic types of loops. A while loop tests a conditional expression, and the body of the loop is executed while the condition remains true. A for loop iterates over a sequence, and the body of the loop is executed for each element of the sequence and until the sequence is exhausted. Here in Komodo, I've opened a working copy of while.py from chapter 2 of the exercise files, and we see a while loop down here starting on line 7, and the condition is n is less than 5. So we've initialized n in the line above, and while n remains less than 5, and of course it starts at 0, which is less than 5, so the condition is true. And you notice that we increment n each time through the loop at the end of the loop, make n plus equals 1. And for each value of n, so it'll be 0, 1, 2, 3, and 4, it will print an element of this list up here. And the elements are numbered 0, 1, 2, 3, and 4. When n gets to 5, it's no longer less than 5. The condition is false, and the loop will finish. And so when I save this and run it, you see we print each of the elements of the words list. For a more practical example, I have a working copy of Fibonacci.py from chapter 2 of the exercise files, and this simply prints a Fibonacci series. So I'll save this and run it, and you can see there's a series of Fibonacci numbers. And this condition here, while b is less than 1,000, is what stops it with the Fibonacci number of 987. A for loop is very different, and here we have a working copy of for.py from chapter 2 of the exercise files. And for many uses, this is far more convenient than a while loop. You notice here on line 6, for I in words, and so we have our same list of words, and for each element of words in order, because it's an iterable. So for each element of words, the variable I will be assigned that element, and the body of the loop is executed, which in this case is simply print I. So you see it's much easier than doing this with the while loop, and when I save this and run it, you see we get exactly the same result. Every element of the list is passed to the print function and printed. And you can see that it's very easy, and this is why you'll see this loop very, very often in the case of containers in Python and other iterables. For I in words is just a whole lot easier than initialize I, test a condition, increment I. So for many uses, this can be a lot more convenient than a while loop. Python provides the two most useful forms of loops, a while loop and a for loop. You'll see many examples of these loops as you continue with this course. Functions in Python serve the purpose of both functions and subroutines in other languages. Here in Komodo, I've opened a working copy of function.py from chapter 2 of the exercise files. And here we have a very simple function with just one line of code in its block. The function is defined with the def keyword that defines a function. Then we have the name of the function, and it will always have parentheses, even if it does not take any arguments. And any arguments are separated by commas inside of those parentheses. And then that argument becomes a variable within the scope of the function. and that variable can be printed in this case. And so here's the call to the function call. We have the name of the function and then the parentheses again. They're not optional, even if there's no argument, and a value. So here we're passing the function the value 47, and it will print the number 47 when I save and run it. And there we have the number 47 in our command output. So if I give it a different number, say 12, and save and run, it prints a 12. If I don't give it a number, then we get an error because the function requires an argument, but we're not giving it one. We can, however, give the argument in the function a default value, say n equals 1, and that way if I do not provide an argument, then it'll default to 1. So now when I save and run, we get, the function works, we get a value even though I didn't pass the value. But still, if I do pass the value, it will use that value instead. Now, in Python, all functions return a value. And so if I say x equals function and then print x, we'll see what this returns. We're not returning it anything explicitly. So by default, it returns the default value of none, which is the absence of value. It's a special keyword and a special value in Python that means the absence of a value. And yet if I give it a return statement, say n times 2, then it will return that instead. And so now it's returned a value of 84. As a practical example, here I have a working copy of primes.py. I'm just going to close this bottom pane so you can see the whole thing. This is a simple example where we assign a value of 5 and we test to see if it is a prime or it is not a prime. And this is the function is prime, and it returns true if the number we pass it is prime number, and it returns false if it is not prime. So if I run this, of course 5 is a prime value, a prime number. And if I give it a 6 instead, then it will say 6 is not prime because 6 is not a prime number. If I want a list of prime numbers, then I can define a function to give me a list of primes. You notice that I have to use the parentheses even though I'm not passing a value to this. It's just going to define a list of primes, and I'm going to say for n in range 100. So this will give us a range of numbers from 0 to 100, and not including 100, because that's the way the range function works. If is prime, and give it that n, then we print n. And I'm going to use a special argument to print that'll have it end the print with a space instead of a new line, because normally print gives us a new line after each printing. This will give us a space instead. And because of the way that some operating systems work, I'm going to flush the output buffer. We'll talk about that later. And when we're all done, we'll just print a new line by itself. So now we have a function that will list primes, and I'm going to call that here, list primes. And again, I have to use the parentheses even though I'm not passing it anything. And when I save and run this, you see we get a list of prime numbers up to 100. So functions are a fundamental tool in Python. They're used for creating reusable code. And you see here in this example, I reused isPrime for two different purposes. They're used as methods and objects, and they're simply used for breaking down code into smaller, more manageable pieces, as I did with list primes here. We'll cover functions in more detail later in the course. In Python, a class is a definition and an object is an instance of a class. Here in Komodo, I've opened a working copy of class.py from chapter 2 of the exercise files. And starting down here on line 4, I'm just going to close that bottom pane so we can focus on the code. Starting here on line 4, we have the definition of a class. And so it uses the keyword class, and the name of the class is duck, and the colon introduces the contents of the class, which in this case we have two functions. Sometimes functions are called methods, and sometimes variables inside of a class are called properties, although Python uses a slightly different definition of properties, so we'll call them class variables here. And so these two functions, quack and walk, are now part of that class. And you'll notice that the first argument for a method inside of a class is always self. And that's not a keyword. You can actually name it something else if you like. I strongly recommend that you use the word self because everybody else does, and then your code becomes readable by everybody else. And that is a reference to the object when the class is used to create an object. And so you'll use that, and we'll show you in a moment how that's used in order to reference the object itself. And so down here in main, we've got a variable called Donald, and we assign it from the class, and that makes Donald an object. And so Donald is now an object of the class duck. And so we use the dot as the dereference operator to reference members of the object Donald. And in this case, we're calling this method quack. And in this case, we're calling the method walk. And so when I save this and run it, you see that Donald quacks and Donald walks like a duck. Now, if we want to, we can put some variables in here, and I can say sound equals quack. And I can say walking equals walks like a duck. Let's give this a couple more A's and an exclamation point so it kind of matches. And instead of these now, we can say self dot, and you see sound, and it's got a V there. The editor knows about this, so it's saying it's a variable. And in print, we can say self.walking. And now when I save it and run it, we get exactly the same result. And I can change it if I want to. I can give it a couple more A's and say walking like a duck. And then when I save and run it, we get those new results. So we'll see lots more examples of this throughout the course, but here you can see how easy it is to define a class and to use it as an object and to give it variables and functions as methods. Classes and objects are very easy to work with in Python. In fact, object-oriented programming is and always has been a focus of the Python language. We'll cover classes and objects in much more detail later in the course. There are just a few fundamental data types in Python. Here in Komodo, I've opened a working copy of types.py from chapter 3 of the exercise files. You'll notice down here on line 4, there's a variable x, and it's assigned the value 7, the constant number 7. And you notice on line 6, I print the type of the variable x. So type is a built-in function that prints the type of a value or variable. And so when I save and run this, you notice that it says that the type is class int. That's the integer type. It's one of the built-in types. Python uses a form of dynamic typing, sometimes called duck typing, where the type of a value is determined by the value itself. In other words, if it walks like a duck, it's a duck. So if I change this value to, say, 7.0, and I save and run it, you see now it's class float. So it's a floating point number. And if I put that in quotes, now it's a string. And so if I save and run this, it says class string. str is the name of the built-in class for the string type in Python. If I change it to the word true with a capital T, save and run, now it's class bool because that's the Boolean type. And if I change it to none, again with a capital N, this is the built-in type for not a value. And so it says class none type, which is the name of that type. So these are the fundamental built-in types. Python is designed to be extensible, so it's easy to create your own types within its object system. And we'll cover these built-in types in more detail in the rest of this chapter. In Python 3, all types are classes, even the built-in types. Mostly this fact is transparent, you'll never notice it. In the case of the string type, it's very useful to know. Here in Komodo, I've opened a working copy of types.py from chapter 3 of the exercise files. We'll go into much more detail about string objects in a later chapter, but for now it's good to understand a few common patterns. First of all, I'm going to change this 7 to the word 7 in a string. You notice that the string is wrapped in single quote marks. And when I save and run this, we have the X is 7 and the types str, which is the internal string type. But it's good to know that the single quotes is a style choice. Double quotes are exactly the same. If I save and run this, you see we have exactly the same result. There is no difference between single quotes and double quotes in Python. In some languages, double quotes are interpolated, single quotes are not, or there may be other distinctions. In Python, there is no difference whatsoever. In fact, you can even do it this way. You can use 3 single quotes. And if I save and run, you'll see there's no difference. What that allows you to do, though, is to put things on several lines. So using 3 quotes, you can actually make a multi-line string. And if I save and run this, you see that the result here, open this up, it says X is 7 with lots of new lines of before and after it. And those single quotes can be double quotes as well. So you'll often see this. These triple quotes are usually made out of double quotes. I know that seems to be the style that most often people use. So if I save and run this, you see our result is still the same. But for now, we're going to go right back to my style choice. And again, it's good to have a default style and stick to it. For my part, I tend to use the single quotes. Probably goes way back to when I was doing a lot of work in Perl, and the single quotes are not interpolated, but the double quotes are. And so I tended to use the single quotes unless I needed the double quotes. Different languages are in different ways. I tend to default to the single quotes. A lot of people do. In fact, most of the Python authors that write the documentation seem to default to single quotes. There's no functional difference, but it's good to be consistent. So pick one and stick with it. Now, as I mentioned, strings are objects, even literal strings. So here I have a literal string, the 7 in quotes, and it's an object. So I can run methods on that object and say I'll choose capitalize here. And when I save and run this, the string in our results now has a capital S. And so instead of capitalize, if I say upper, it'll now make it all uppercase or lower. Of course, the string was lowercase to start with. In fact, I can even put some place markers in it and use format. And when I run this, it'll say 789 like that. Now, the format method has a number of options. And again, we'll get into more detail with this later on. But it's good to understand what it does. These are positional arguments here. And so they're in exactly the same position. If I have 2 of these and I have 2 arguments, they will replace them in order. So that'll be 7, that'll be 8, and that'll be 9. I can specify positional arguments by putting a 0 in this one and a 1 in this one, and now they'll swap around in the result. You see now it says 7, 9, 8. I can put a colon after this and say I'll left adjust this one 9, and I'll right adjust this one 9. And when I save and run this, you notice that now there's 9 spaces to the right of this one and 9 spaces to the left of that one. So I can put these in quotes, and I'll use double quotes here, because you can use double quotes inside a single quoted string, and you can use single quotes inside a double quoted string without escaping them. Now, if I save and run this, you see that we have the spaces. So what we've done is we've left aligned this one in 9 spaces, and we've right aligned this one in 9 spaces. If I want leading zeros, I can put a 0 before this, and it'll fill with zeros. In fact, if I put a 0 before this one, it'll still fill with zeros to the other side. And so here I've got 9 with the zeros filled after it and 8 with the zeros filled before it. And you'll notice that it's 9 spaces total. I put that 9 there. It's not 9 spaces after and 9 spaces before. So there's 8 spaces after and 8 spaces before, because it's 9 spaces for the entire number. So if I make this number larger, you notice that it fills in, but it takes up the same amount of space, those same 9 digits. All right, so I'm just going to put this back a little bit. and save and run that. And you see we get the brackets if we're not using any formatting. Now I can say dot format and say 8 and 9. And when I save and run that, of course, we get the 8 and 9. Or instead, I can make this all an F string. And let's create a couple of variables. A equals 8 and B equals 9. And I can put the A and B inside of these and save and run it. And we have that same result. Now, what I've done here is instead of putting the dot format class after the string, I simply use this F before the string, and that makes this what's called an F string. And F strings are available in Python 3.6 and after. They are not available in any of the earlier versions of Python. So Python 3.6 is just a year or so old as of the time that I'm writing this. But you have it if you've installed it according to instructions in our introductory chapter here in this course. And so these F strings should work for you. Now the F strings, they use the format method on the string class, so they work exactly the same here. Instead of the positional argument here, you have the name of the variable or the value itself. Of course, I can put in a value here, and when I save it and run it, it'll work just the same. But usually you'll use it with a variable of some sort, and so I can still put in the colon, and I can left align this 9 spaces and right align this one 9 spaces, save and run. And you see that we get exactly the same results. I can put in a leading 0 here and put in a leading 0 there, and we have exactly the same results. So F strings work pretty much exactly like strings using the format class. So there are many more string functions and many more formatting options, and we'll cover all of that in a later chapter. Python 3 has 2 basic numeric types, integer and floating point. There are other types derived from these, including the built-in complex type. In fact, because everything is an object in Python, you can derive your own types. Here we're going to talk about integer and float. Here in Komodo, I've opened a working copy of types.py from chapter 3 of the exercise files. And you notice down here on line 4, x equals 7, and 7 is an integer. So if I save this and run it, you see it says class int. And if I multiply this by 3, save and run, we now have a value of 21, and it's still a class int, so it's an integer. On the other hand, if I say 7.0 and save and run it, we now have class float, which is a floating point number. Or if I say 7 times 3.14159, I save this and run it, we now have a floating point value because we used a floating point number in our calculation. On the other hand, if I divide 2 integers, say 7 divided by 3, when I save and run this, I have a floating point number, even though I divided 2 integers. This is a behavior that's new in Python 3. In Python 2, it would have done an integer division and given me the result without the remainder. I can still get that result by using a double divide sign. If I save and run this, I now get 2, because you can fit 2 3s in 7 with a remainder of 1. And if I use the modulo operator, the percent sign, then I get that remainder. And these types are, of course, int. Now here's an interesting problem. If I say 0.1 plus 0.1 plus 0.1 minus 0.3, you would expect that my result would be 0. When I save and run this, you notice that my result is 5.55, etc., e minus 17. That's all 17 places to the right of the decimal point, or rather moving the decimal point 17 places to the left. So it's a very, very minuscule number. It's almost 0, but it's not 0. This is especially a problem when dealing with money. You remember when we do arithmetic in school, if we add these 3.1s and we subtract 0.3, we're going to get a 0, and it's not going to have a bunch of numbers 17 places to the right of the decimal point. This is the difference between accuracy and precision. Because of the way that the computers do floating point, they're sacrificing accuracy for precision. And so it may do this arithmetic correctly to 17 decimal places, which is the precision of the floating point processor inside the computer. But it is not accurate. Accuracy is the true value of a calculation. As an illustration, here is an actual cash register. I took this photograph at a movie theater in Phoenix, Arizona in December 2011. And you'll notice that the total cost of my water, because I bought water in a movie theater, which is ridiculously expensive, was $13.50 and a little bit more. This is 13.50001, and it made everything wrap around weird on the screen because the screen was formatted for 2 decimal places, and instead somebody forgot that floating point numbers don't work well with money. And in fact, that's my point here. You don't want to use floating point numbers for money because you end up with those kinds of problems, because 10 cents plus 10 cents plus 10 cents minus 30 cents needs to be 0 cents in order for books to balance properly. So how do we solve this problem? Python comes with a built-in module called import. And so I'm going to say from decimal, import everything. And now here I can say A equals decimal. I now have a type 0.10. So that's 10 cents in decimal. And you notice I have to put that in quote marks. It's going to convert it from a string because we don't want to pass it a floating point number, because a floating point number isn't accurate. It has precision, but it doesn't have accuracy. And so I say B equals decimal 0.30. And now I can say X equals A plus A plus A minus B. And when I save and run this, you notice that the result is 0.00, which will balance your books really nicely. And the type is class decimal dot decimal. So it's the decimal class from the lowercase decimal library. So you're going to want to use something like this. It can either be this module or one that you write yourself or another one, but you want to use a proper decimal arithmetic module when you're dealing with money. So understanding the numeric types can save you a great deal of trouble. For many purposes, the simple integer and float types will work fine. For other purposes, the decimal module will be necessary, or you may want to derive your own class. The bool type is used for logical values and expressions. Here in Komodo, I've opened a working copy of types.py from chapter 3 of the exercise files. And if I save this and run it, you'll see I get x is 7 and class int. And so that's coming from line 5, which prints the value of x, and line 6, which prints the type of x. Here in line 4, I assign a value to x, and if I assign it the special literal true with a capital T, you'll see when I run it that the class is bool, and the representation in the string is the word true. And likewise, if I use false here, I also get the class is bool. So the bool type is for logical values and expressions. For example, here, if I say 7 is greater than 5, I'll get a bool type true. And I'll save and run that. X is true. This is because the comparison operators return true or false in the bool type. It's worth noting at this point, and I have a reason for this, we're going to use this, and you'll need to understand that there is a special type, none, and it's the none type. If I save this and run it, you see the value is none and the class is none type. The none type is used, and it has only one possible value, which is none, and this is used to represent the absence of a value. And there's a reason I'm showing you this at this point. If I come down here and I say if x, print true, else print false, and these are strings here. So when I save and run this, you'll notice that with the value of none, the logical test here in if returns false. So it's worth noting that there are a few things that evaluate as false. Any numeric 0, so if I save and run this, x is 0, class is int, and the test is false. Any empty string, so if I just try this, I have an empty string, class string, and it evaluates as false. So if I put anything at all in that string, it's no longer false. So I'll save and run this, and it's now true. And if a number is not 0, again, it'll return true. It'll evaluate as true. So like many languages, you can use any type as a logical value as long as you know the rules. None evaluates as false. 0 evaluates as false. And an empty string evaluates as false. Pretty much anything else, at least in the default types, will evaluate as true. So the bool type has two possible values, true and false, and additionally many other types may be used as logical expressions and will be evaluated as false if they're effectively 0 or empty, otherwise they will be true. We'll see other examples of this behavior later in this course. Python provides some built-in sequence types including lists, tuples, and dictionaries. Here in Komodo I've opened a working copy of sequence.py from chapter 3 of the exercise files. A list is created with square brackets, like this, here on line 4. And if I save and run this, you'll notice that we get this result, I is 1, I is 2, etc. The for loop is sequencing through the list, and for each item in the list, it assigns I the value of the item, and I is used in the print function. A list is a mutable sequence, so I can reassign one of the values after I have assigned it. I can say x sub 2 equals 3, and so I'm accessing with this index in the square brackets, I'm accessing a particular specific item in the list, and I'm going to change its value to 42 like that. And so when I save and run it, you'll see that the item number 2, which is the third item, because the index starts at 0 for all sequence types in Python, and I've reassigned that to the value 42. So I can say item number 0, or all the way up to item number 4, and it will reassign that value. Now, on the other hand, a tuple is exactly like a list, only it's immutable and it's indicated by parentheses. And so if I try and run this with a tuple instead of a list, you notice I get the error, type error, tuple object does not support item assignment. That's because a tuple is not mutable. You cannot change it, or sometimes it's referred to as being immutable. So if I remove this line and run it again, you'll notice that it works exactly like the list. I find that it's generally a good idea to favor the immutable type tuple over the mutable type list, unless you know that you need to change the elements in the list. So I'll tend to use the parentheses by default and only use the square brackets when I know that I need to change something. You can also create a sequence using range. And so instead I can say here range sub 5 like that. And when I save and run it, again, it starts at 0 and it ends at the number before what you specify. So that end is actually the last item minus 1. So when I specify a 5, it'll end at 4. If I specify a 10, save and run that, you notice I get a sequence only up to 9, and it also starts at 0. I have to scroll backwards to be able to see that. There's actually 3 possible parameters for range. If you give it just one parameter, it takes us as the end mark and it starts at 0. I can change the start. I can say start at 5 instead. And when I save and run this, you notice I get 5, 6, 7, 8, 9. Or I can say end at 50, but step by 5. And when I save and run that, I get 5, 10, 15, 20. So that third parameter is a step by. If you specify all 3, they're start, end, and step. And if you specify just 2, it's start and end. And if you specify just 1, it's just end. And so if I save and run this again, I get 0, 1, 2, 3, 4. like the tuple, a range is not mutable. So if I try to say x sub 2 equals 42, save and run, I get this error. Type error range object does not support item assignment because it's immutable. If I want a mutable list, I simply construct a list with the result from range using the list constructor like this, and save and run it, and now I have 0, 1, 42, 3, and 4. A dictionary is a searchable sequence of key-value pairs, and you construct it like this. And so that's a dictionary, and if I just save and run this, you notice that I get I is 1, I is 2, I is 3. I'm just getting the keys, I'm not getting the values. If I want to get the keys and values, I can say in my for loop, key comma v in x dot items. So that'll actually return a 2 tuple of each of the items with the key and the value. And then I can print it out like this. I can say key and value like that, and it will print the key and the value for each element in the dictionary. Now, each of these values, the keys and the values, can be any type. And the same is true for lists and tuples. Any element can be any type. And dictionaries are mutable, so I can come up here and I can say x sub 3, and use the key to index it, equals 42. And when I save and run it here, you notice that key 3 now has a value of 42. So this is an overview of Python's built-in sequence types. And you'll see a lot of examples of these in the rest of the course. These built-in sequence types are very useful and flexible. In Python, everything is an object, so a type is the same as a class. Here in Komodo, I've opened a working copy of types.py from chapter 3 of the exercise files. And down here on line 4, I'm going to create a tuple with 5 elements. I'm going to say 1, 2, 3, 4, 5. And when I save and run this, you notice that line 5 prints a representation of that tuple. And line 6 says that the type is class tuple. Now, where this starts to get interesting is when I make this tuple into something else. We'll change this 2, a string that says 2. We'll change the 3 to a float. Change the 4. We'll just make that a list. The number 4 and a string 4. And we'll leave the 5 alone. So when I save and run this, now you'll notice that the string representation printed out on line 5 is exactly this structure that I've created there, and line 6 still says type tuple. But if instead I ask, well, what's the type of that second element, which would be element number 1? Remember that these indices start at 0. And if I save and run this, it now says, well, that's a string. So this is useful information. I can inspect any element in my structure, and I can say, well, what type is that? On the other hand, if I bring this back to the type of x, and let's just duplicate this and make a y that's got exactly the same stuff in it, and I'll ask for type of x and type of y, we get the same result for both of them. But instead of type, if I ask the ID, and I'll do that for both of these, I save and run, you'll notice I get 2 different unique numbers. So these are 2 different objects. ID function returns a unique identifier for each object. Now, if I ask for the ID of x sub 0, I have that literal number 1 there, right? And y sub 0 also has a literal number 1. Then we save and run this and we find out that they're exactly the same because there is only one literal number 1 object. There's no need for Python to create 2 different objects for the literal number 1. So I also have an is operator, and I can say, well, are these 2 different things exactly the same? I can say if x sub 0 is y sub 0. This checks to see if they are exactly the same object. So I print, yep, if they are, and else print nope if they are not, and I save and run that, and they are the same object. But if I'm just asking if x is the same object as y, then, oops, that's not where I wanted to do that. Well, I can do that anyway. I want to do that here. If I just want to know if x is the same object as y, then I can save and run, and I can see that, nope, they are not the same object, even though they have all the same values. Now, this is all very useful, but if I want to know, is this particular object a list or is it a tuple? None of this is going to help me. I can't say if type of x is equal to tuple, because that's just never going to work. It's going to say nope. On the other hand, there's a special function called isInstance. isInstance, if isInstance x tuple. Save and run, and you'll notice it says yes, it is. It says, yep, x is a tuple. Is x list? Well, I can say elif. Yeah, it's not exactly right, is it? It's like this. I can say print list, and here I can say print tuple. Now, if I save and run this, I can see that x is a tuple. But let's make y a list instead. And I'll come down here and I'll test for y. Save and run, and we see that y is a list. So if you want to know, for instance, you're going to handle different types differently. If a particular object is of this type or of that type, this is the way that you do it. You use isInstance. If you want to print out what type something is, then you can use the type function like this. Save and run, class tuple, class list. And that'll print out that value, although that's not something that you can easily test against. For that, you use isInstance. And if you want to know exactly what the specific ID is of a object, you can use the ID function, and that will print their IDs. And you can use the is operator if you want to know if two objects are the same object. So these functions work by using Python's class introspection, and they do come in handy. We'll see examples throughout the rest of this course. The Python syntax for conditional statements is consistent with the rest of the language. Here in Komodo, I've opened a working copy of conditional.py from chapter 4 of the exercise files. This is an example of the conditional statement in Python, and it should look familiar. We have if, elif, and else. If and elif require a condition. In this case, we're just using the Boolean constant true and the Boolean constant false. And else is optional. So if I save this and run it, we see if is true. But if I make that false, the execution should go all the way to the else, and we have neither is true. And if I make the elif true, then it has elif true. Of course, I can have as many elifs as I want to. So we'll number them. Elif 1, elif 2. Let's move this down a little bit so we have more room to edit. 3 and 4. And I can just pick one and say I'll make this one true. And of course, it'll say elif 3 is true. So you can cascade the else ifs to as many as you want. And this comes in handy when you want to do something like this. X equals 5. If x equals 0, then 0 is true. And we need to make that a double equals. If x equals 1, and 1 is true, or we can just leave these numbers here because those will match up. And so this works very much like a switch statement does in other languages. And when I save and run this, we see that elif5 is the one that is true. And of course, if we change this to 42, then we get the none of them are true. So the conditional statement in Python is simple and easy. It uses the familiar if, else, elif keywords and the typical Python indented block syntax. Python tends toward a minimalist language, and as such, it provides a minimally complete set of operators for use in conditional expressions. It has comparison operators for equal, not equal, less than, greater than, less than or equal, and greater than or equal. It has logical operators for and, or, and not. It has identity operator that tests if two objects are the same object. And so it has is and is not. And it has a membership operator, which is true if a variable is a member of a collection. So it has both in and not in for membership. These operators are commonly used in conditional expressions. You'll see many examples throughout the rest of this course. Beginning with version 2.5, Python includes a ternary conditional operator. It's important to note that this operator does not work in versions of Python previous to Python 2.5. Of course, we're in Python 3.6 here, and so we can demonstrate it. Here in Komodo, I've opened a working copy of ternary.py from chapter 4 of the exercise files, and this has a simple example of the ternary operator. So down here on line 5, we assign x to be this string, feed the bear now, if hungry. And we have this hungry variable above, which is set to the logical value true. So that's being tested here in this if clause. And there's an else that says, do not feed the bear. So if the bear is hungry, then the string will be feed the bear now. And if the bear is not hungry, then it will be do not feed the bear. So when I save and run this, it says feed the bear now. And if I set hungry to false, and remember 0 works fine for false, I save and run and it says do not feed the bear. Now it's important to note that all of this is required. If you're going to have the ternary conditional operator, you must have both if and else. You must have both clauses. Of course, if you want to, you can have else set it to none. And so when I save and run, it'll say none. But you must have an else clause. It does not work with just the if clause. The ternary conditional operator is used occasionally, but it can be very convenient in some circumstances. Python has a full set of arithmetic operators, and they're listed here: addition, subtraction, multiplication, division, integer division, remainder, exponent, and the unary, negative, and positive operators. Here in Komodo, I've opened a working copy of arithmetic.py from chapter 5 of the exercise files. And you see we have a couple of variables, and then we perform arithmetic on them and display the result. So first we have the addition operator, and when I save and run this, you see the result is 5.3 equals 8. And we have the subtraction operator, so 5 minus 3 when I save and run is 2. And the multiplication operator, my editor does weird things when I do that. I save and run, and the result is 15. And the division operator, when I save and run that, you notice that the result is no longer an integer, even though the two operands are integers. When I divide, I will always get a floating point. This is new behavior in Python 3. Python 2 does not work this way, so it's worth taking note of. If I want to get the integer division, then I use 2 slash marks for the operator, and when I save and run, I get a result of 1, which is 5 divided by 3 without the remainder. If I want the remainder, I use the percent sign, which will give me the remainder or the modulus. And when I save and run, you notice I get that remainder of 2. There's also unary operators for negating and leaving an operand positive. And so if I say z equals minus z, then I get a result here of minus 2. And if I say z equals plus z, then I get the 2 by itself. And even if the number was already a negative, when I say z equals plus z, it simply doesn't negate it. So that's just there for decoration. It doesn't really do anything to the operand. So these are the arithmetic operators in Python. We'll cover more operators in the rest of this chapter. These are Python's bitwise operators. There's AND, OR, XOR, shift left, and shift right. These operators operate on bits. They're not the logical operators used for the conditional constructs. These are bitwise operators that operate on numbers, and they operate on the individual bits in the numbers. We'll take a look now at how that works. Here in Komodo, I've opened a working copy of bitwise.py from chapter 5 of the exercise files. And I'm just going to go ahead and run this so you can see what it is that's going on before we talk about the individual operators. If you come down here, I have two variables, x and y, and these variables are initialized using hexadecimal literal numbers. And so the first one is 0a and the second one is 02. And then I'll operate on them using an operator. In this case, it's the AND operator. And then I print it out twice, once in hexadecimal and once in binary. And you'll notice that I'm using fstring, and I'm using these format controls, these format specifiers, in this case 02x, and that gives us 2-character string, and it's in hexadecimal and it has a leading 0. So the 0 gives it the leading 0, and the 2 says that the field is 2 characters wide, and the x is for hexadecimal display of an integer value. And you notice I pass it the x here, and I pass it the y here, and the z here for the result. So I do the same thing in the second print call, also using an f string. Difference here is that now the field is 8 characters wide, still has a leading 0, and in this case it's a binary representation of the value. So if we look down at our results, you'll see that x is 0a in hexadecimal, and in binary it's 00001010. So the first 4 zeros are the hexadecimal 0, and the second 4 digits, 1010, is the number a, which in decimal is a 10. And so this allows us to see bitwise what's happening here. So because the operation is an AND, you'll notice in x, 1010, and y is 02. So we have 2 bits set here in the x and only 1 bit in the 2. So the AND operation will only set a bit if both of the operands have a bit set in that position. And so this fourth position here, counting from the right, this fourth position here has a 1, and it does not have a 1 here in the y, and so in the z that does not get set. The only one that gets set is that 2, the second bit. All right, so hopefully this is clear at this point. We're going to go ahead and look at some of the other operators. If I take this and change it to a vertical bar, which is the OR operator, and if I go ahead and run this, you'll notice that all of the bits are set in z, because it will set a bit if either the left operand or the right operand has a bit set in that position. And so that's the bitwise OR. If I change this to a 5, I'll save and run here, we get all the bits set, because a 5 is 0101, whereas an A is 1010. So between the two of them, they've got all of the bits set. So XOR, the exclusive OR, is the caret symbol, and exclusive OR means that the result will have a bit set only if one or the other, not both, operands have that bit set. So I'm going to change this here to a F. And F will have all the bits set. If I save and run this, you notice that it has all the bits set in the right-hand operand. But in the result, only the bits are set in the case where one and not the other. So that's a 5, right? So looking at them bit by bit, The left-hand operand has this bit set, and so does the right-hand one, so that is not set in the result. It's only if one is set and not the other. So this is an effective way to basically flip the bits. By XORing with F, the A bits are flipped, and the result is a 0, 5. We also have shift left and shift right, so I'm going to change this right operand to a 1, and I'm going to use the shift left operator, which looks like that. And when I save and run, you see that the bits here are shifted left by 1. So it's 1010 here, and here it's 10100. And likewise, we have a shift right operator, which looks like that. And here it'll shift the bits to the right. So the A gets shifted to the right, where it becomes a 5. So these are the bitwise operators that are available in Python. It's a fairly complete set, and we'll cover more operators in the rest of this chapter. These are Python's comparison operators, and there's a complete set of them: less than, greater than, less than or equal, greater than or equal, equal and not equal, and they compare the value of two operands. Let's take a look at how this works. Here in Komodo, I've opened a working copy of comparison.py from chapter 5 of the exercise files, and you notice that it's pretty simple. I have two variables and I have an if-else, and then there's a comparison operator in the if right there. And so in this case, it's using the less than comparison operator. So the condition will be true if the left-hand operand is less than the right-hand operand. And so in this case, it is x is less than y, 42 is less than 73, so it should print comparison is true. And when I save and run this, you see it says comparison is true. Now, if I change this operator to a greater than operator and save and run, you see that the comparison is now false. There's also less than or equal to, so if I use less than or equal to and save and run, it is true. And that's also true if I change the y to a 42. I still get a comparison is true. And the same is true of greater than or equal to. If I save and run this, you see that that is also true. Whereas if I make this 73 again, it is now false. There's also the double equal comparison operator. This checks if the values are the same. And so when I save and run this, it says false. But if I make this a 42 and save and run, now the comparison is true. And there's the not equal operator. So that's with an exclamation point and an equal sign. And if I save and run this, you notice that that is false. But if I change 42 back to 73 and save and run, and now the comparison is true. So these are the comparison operators in Python. They're pretty straightforward, and we'll cover more operators in the rest of this chapter. These are Python's Boolean operators. And it's an interesting set because it includes the traditional and or not. It does not have the traditional XOR, which is not hard to create on your own. And it has a few others for testing if a value is in a set or not in a set, or if testing the identity of two operands, whether they're the same object or if they're not the same object. So it's a little different than you might be used to in some other languages, but it's all very useful. So let's take a look at how these work. Here in Komodo, I've opened a working copy of boolean.py from chapter 5 of the exercise files. And you notice we have some variables set up here starting on line 4, and then starting on line 9, we have an if-else. And the condition uses these Boolean operators. So in this case, we're testing A and B, which is true and false, which the result of which will be false because for and to be satisfied, they would both have to be true. So when I save this and run it, you see expression is false. If I change this operator to or, A or B, now it'll be true because A is true, even though B is not. And that result is now true. I also have the unary not. And so if I say if not B, because B is false, the expression is now true. And likewise, if I say if not A, we get the expression is false. Now we can test if y is in x, because x is a collection, and so we have a value in y, and we can test if that value exists in the collection by saying y in x. And if I save this and run it, you see the expression is true. Instead of y, if I say leaf, if leaf in x, it'll be false because we do not have a leaf in x, but we do have a tree. So if I say tree, we can see that expression is true. We can also check if y is x sub 0. And this is interesting because you have two literal strings, but if I test their identity, save and run this, you notice that the result is true. And this is because strings are not mutable. And so there's no reason, if you have two literal strings with exactly the same variable, there's no reason to carry around two separate objects. So it gets optimized into one object. So that result is true. They're actually exactly the same object. And we can see that if we print out their IDs. ID of y and print ID of x sub 0. Save and run that, and you see they both have exactly the same ID, and they are indeed the same object. Likewise, I have is not, and if I save and run that, you'll see that expression is false, but if I say x sub 1, then that expression is true because bear is not bunny. So these are the Boolean operators available in Python. Operator precedence describes the order in which operators are evaluated in a compound expression. For example, here's a simple expression, 2 plus 4 times 5. Do you apply the multiplication first or the addition? If you multiply 4 times 5 and then add the 2, you get one result. So 4 times 5 is 20, plus 2 is 22. But if you add the 2 plus 4 first, 2 plus 4 is 6, times 5 is 30, you get an entirely different result. This is why operator precedence is important. If you remember your high school math, then you know to do the multiplication first and get the correct result. In Python, operators have precedence. This is a chart of operator precedence in Python. The higher precedence operators are at the top and the lower precedence are at the bottom. In many cases, the order of these operators is obvious and follows the same rules as the math we learned in school. In other cases, they may not be so obvious, so it's always a good idea to use parentheses to explicitly specify the order you intend an expression to be evaluated. You can find a complete chart of operator precedence in the Python documentation. Python has two basic forms of loops, while loops and for loops. A while loop uses a conditional expression to control the loop. When the condition is true, the body of the loop is executed. When the body is complete, the condition is tested again, and if the condition is still true, the body is executed again. The loop continues as long as the condition is true, and when the condition is false, the loop ends, and execution continues with the lines of code after the loop. A for loop uses a sequence, like an iterator or a list, tuple, or other collection type, to control the loop. The body of the loop is executed for each item in the sequence, and when the sequence is exhausted, the loop ends. We will cover both of these types of loops in this chapter. Python's while loop uses a conditional expression to control its loop. Here in Komodo, I've opened a working copy of while.py from chapter 6 of the exercise files. And you see here's our while loop down on line 7, and the condition, the conditional expression, is while this PW variable is not equal to the value of the secret variable. And the body of the loop is this one line of code which assigns the PW variable from the input function, which inputs a line of text with a prompt. And so the secret variable is set to a string. It says swordfish in all lowercase. And the PW variable is set to the empty string. And so when I save this and run it, it asks me what's the secret word, and I can put my cursor down here and I can type something in. And when I press return, you see it asks me for the secret word again, because the secret word was not correct. And if I type something else in, it's still not correct. Try secret, still not. Oh, I'll type swordfish. And now the loop ends because the conditional expression is no longer true. Password is equal to secret when I type in swordfish, and that ends the loop. So obviously you can use any conditional expression here. You just need to make sure that whatever it is you're doing in the loop will eventually resolve that and make that conditional expression no longer true. Otherwise, you'll end up with an endless loop. So the while loop uses a conditional expression to control the loop. It is simple and elegant, and you'll see many examples of it throughout this course. And I'll show you some additional ways to control the loop later in this chapter. The for loop uses a sequence like an iterator, list, tuple, or other sequence object to control the loop. Here in Komodo, I've opened a working copy of for.py from chapter 6 of the exercise files. And here we have our for loop, which uses this tuple to supply its items, and it assigns each item to the variable pet and then prints it. And so when I run this, you see we get, open this up a little bit so we get the whole thing. We get our 5 items from the tuple: bear, bunny, dog, cat, and velociraptor, all cute little animals. So obviously this can be any sequence. It can be a range is very common. You can say range 5, and that's actually supplies an iterator. And so when I save and run, we get 0, 1, 2, 3, and 4, or any sequence or any iterator. This is extremely powerful and useful and convenient, and you'll see it often. In many cases, you'll see it more often than the while loop. I know that I tend to use this a lot more often than I use a while loop in my code. I'll show you additional ways to control the for loop later in this chapter. Both the while and for loops have some additional controls that are worth understanding. 3 additional controls are available: continue, break, and else. The continue clause is used to shortcut a loop and start it again as if it had reached the end of its body of code. The break clause is used to break out of a loop prematurely. Execution will continue after the entire loop structure. And the else control is not common in other languages, so you may not have seen this before. The else block executes only if the loop ends normally. It will not execute if a break is used to end the loop. These same controls are available for both while and for loops. For example, here in Komodo, I have opened a working copy of while.py from chapter 6 of the exercise files. And I'm just going to add a couple of variables here. We'll have an auth equals false, and that'll be true if the user is authorized. We'll have a count to count the number of attempts, and a max attempt for the maximum number of attempts that we'll allow. And we'll go ahead over here and we'll make this an F string, and we'll add the count in front. And so now when I save and run, oh, actually, no, I want to stop that. So I'll press my little stop button over here. I need to increment the count. So count plus equals 1. So it'll start with number 1 for the first count. And if I say, no, that's not right, 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 you notice that it keeps going forever until I type swordfish. And for security purposes, that's not always a great idea. So instead, I can say if count, we want to put this up here actually. If count is greater than max attempt, and I'll just put a break on the same line there. So now, if I try and run this, X, Y, Z, wrong, wrong again, it stops. And I can put in a nice little message At the end here, I can say print and use a little ternary conditional operator and say authorized, if auth, else, calling the FBI, right? And so now if I try this 5 times, 1, 2, 3, 4, 5, it says calling the FBI because I didn't get it right. But if I do get it right, well, oh, I never set my auth to true. Auth gets set to true in the else clause because else only gets executed if the while loop exits normally where the condition turns to false, right? And so I can say auth equals true because I know that I've tested up here on line 10 that my password matches. And so now when I type in swordfish, it says authorized. But if instead I say X, Y, Z, X, Y, and ZZ, it says calling the FBI. So we've seen break and we've seen else. Let's take a look at continue. And all continue does is it shortcuts the loop. It sends us back up to the top of the loop and tests the condition again at whatever point. So if I say if count is equal to 3, continue, now what happens is, let's say X, Y, now I get 1, 2, 4. You notice my number over here, 1, 2, 4, because 3 continued the loop and it went back up and it tested the condition again without printing out the prompt. And so I only get 4 tries instead of 3. So hopefully this makes all of this clear for you. Break will break all the way out of the loop and skip the else clause. Continue will shortcut the loop and go back up to the test without finishing the body of the loop, so it won't execute this line 14. And the else clause only gets executed when the condition is no longer true and the loop exits normally, and that'll set auth to true. These same controls work in a for loop. Let's take a look at that. I have a working copy of for.py from chapter 6 of the exercise files, and we've seen this before. When I run it, it prints out this tuple, bear, bunny, dog, cat, velociraptor. So for example, here I can say if pet equals dog, continue. And now when I run it, it'll skip dog. It won't print dog because it shortcuts the loop, right? And it goes back to the control just like it does in the while loop. And I can say if pet equals velociraptor, break. And so I'll print an else down here. Print that is all of the animals. And when I run it now, because it hit velociraptor and it hit break, it did not print that as all of the animals. But if I don't have this break in here and I save and run, then it says that is all of the animals because it exited normally by exhausting the list. And if I, of course, take out the continue, then we have all 5 of the animals. So the continue, break, and else controls can be extremely useful. Even if you don't use them all the time, they are important to understand. Functions are the basic unit of reusable code in Python, so let's take a look at how they work. Here in Komodo, I've opened a working copy of function.py from chapter 7 of the exercise files. I want to start down here at the bottom because this is relevant and we have more context now to describe this in more detail. We've already covered conditional expressions and if and blocks and things like that. And so I just want to describe how this works in a little bit more detail. So you notice it's an if statement and the colon is right here, and on the same line we have a function call to main. And so with an if statement, you may have the code on the same line as long as it's just one line of code. It's normally frowned upon, but this is one case where it is commonly done this way. And then we have this conditional expression here, which compares using the double equal to test for equality, for value equality, the special variable name with double underscores on either side against a string literal which says main with double underscores on each side. So this name variable, this special variable name, will return the name of the current module. So if this file had been included in another execution unit by the import statement, in other words, if somebody had typed import and the name of this file, then this would be running as a module, and this name would have the name of the module here. But it's not running as a module. Nobody has imported it, and it's running as the main unit of execution. And so because of that, then this main value is a special value, which means, no, this is not imported, this is the main file. And so we test for that, and you'll see later on when we start talking about modules how this can come in particularly handy, but it's often used for this purpose, because this calls main, which is defined up above, and that's okay because you can call a function if it's been defined beforehand, but main then calls kitten, which is defined after it. And so if we didn't have this, and we didn't have a function main, but we had a function defined after it, we would not be able to call it. And so that's called forward declarations, and Python doesn't support forward declarations. And so this is the standard workaround for that, and you'll see it a lot. In fact, it's so common that Komodo here, it has code completion for it. If I type if and 2 underscores, you notice that there's a number of choices, and one of them is that line of code exactly, and I can just type in main, and boom, it code completes that for me. That's just to show you how common this pattern is. You'll see this a lot, especially in modules. And so now if I save this and run it, you see it says meow. That's because this if calls main, which is up here, and this main calls kitten, which is a function defined here, and that calls the print function, which prints meow. Now, a function definition looks like this. It has the keyword def, and then the name of the function, and a pair of parentheses and a colon, and then a code block. And so we've seen that pattern before, and that's very, very common. I can, if I want to, I can put a variable or a value or something here. I can put in the number 5, and then down here I can capture that by putting a variable inside the parentheses. So the parentheses are used for passing parameters. And if I want to, I can make this an F string, and I can print out that N and save and run. And now that 5 is being printed out by that print statement. And so obviously, if I change it to a 3, it'll print out a 3 there. So that's how you pass parameters to a function. And obviously you can put in a comma and pass more than one parameter if you wanted to. And you could capture all of those in the same way in the function. All functions also return a value. So if instead here, and let me just remove those for now because we're not going to use that. If I wanted to, I could say x equals kitten, and then I could print the value of x. And when I save and run, it says none, because the function is not explicitly returning a value. The value that it does return is the special none value. So all functions return a value. If you don't specify the value, they will return none. If instead I wanted to return the string, I can do that. And now this print statement here on line 6 will print the meow. So Python has no distinction between a function and a procedure. Some languages do. Some languages consider a function something that returns a value and a procedure something that does not return a value. In Python, all functions return a value even if the value is none, so there's no distinction between functions and procedures. Python functions are simple and powerful, and we'll get into the details in the rest of this chapter. Function arguments in Python are fairly straightforward. There are a few details that are worth noting. So here in Komodo, I've opened a working copy of function.py from chapter 7 of the exercise files. And if I go ahead and run this, you notice that down here at the bottom we call main, and then main calls kitten, and then kitten calls print with the literal string meow, and that prints the string meow. Now, if I want to pass an argument to kitten, I can do that like this. I can put in a number 5, and then down here in kitten, in the parentheses, I can give it a variable name, and then I can print that variable, or I can do whatever I want with it. And you notice that it prints. I can pass multiple arguments, 5, 6, and 7, by separating them with commas. And likewise, I can say A, B, and C. and I can print them, A, B, and C. And when we run this, we get the 5, 6, and 7 printed. If I don't pass enough arguments, in other words, if I pass a smaller number of arguments in the function call than are expected here in the function definition, then I'll get an error. When I run this, you see it says type error, kitten missing one required positional argument, and it tells us which one, but actually it doesn't know which one. It just assumes it's the last one. On the other hand, I can give that last one a default value, and now when I run it, it no longer requires 3 arguments. It'll accept 3 arguments, so there it's printing the default value of 0, but if I actually give it a 7 and run it, now it prints the 7, and I can give default arguments to however many of these I want to, and save and run that, and it's printing the default arguments. Any arguments with defaults must be after any arguments without defaults. So in this case, I have an A there without a default, and B and C have defaults. If I were to try to have another one that doesn't have a default, even if I were to give it a value, you see I still get an error. It says non-default argument follows default argument. That's a syntax error, and that's because arguments with defaults must be at the end of the list. And that's really so that the interpreter can understand the argument list. It actually makes sense when you think about it. I consider it a best practice that if any of your arguments have default values, that you provide defaults for all of them. Obviously, that doesn't make sense in all cases, but in most cases, that's a really good rule of thumb. Now, here's where things get tricky. I'm just going to go back to having one argument here. And we'll save and run that, and we'll see that that works. And I'm going to replace this with a variable, and we'll save and run that. We see that we still get 5. Now I'm going to print this. I'm going to use an F string here. In main, x is x. And I have to use the same kind of quote marks, don't I? Oops, there we go. And now when I run this, it says in main, x is 5, and that's after the function call. And if I come down in here and I say a equals 3, we save and run this, we notice that it prints 3 in the kitten function, and x is still 5 in the main function after the function call. And so this is what they call in the Python documentation call by value. And in most call by value languages, when you pass a variable to a function, the function operates on a copy of the variable. So the value is passed, but not the object itself. And this is an important distinction, because if the object were actually passed, then if I were to change it here, it would also change there in main. And you notice that it doesn't act like that in Python. Well, that's actually not entirely true. And here's where this gets tricky. Integers are immutable. And so this is an integer because I've initialized it with an integer. And if I were to come down here and print the ID of x, we see that it has that ID there that ends in 216. And if I come down here in kitten and I print the ID of A before I operate on it, you notice, oops, printing A, I want to print the ID of A. You notice that it's exactly the same, but here's where it gets funny. If I print the ID of A after it gets changed, it's now got a different ID number. And none of this is really what we'd expect in call by value. If what was being received by kitten was actually a copy of what was being passed to kitten in the calling function, we would expect this to have a different ID number. But it has exactly the same ID number. So something funny is going on here. And here's what it is. If I take two variables and I assign this same immutable value to both of them, and this is different behavior with mutable values. So I print the ID of both of these, and I'm just going to comment out all of this other stuff so that we're not confused here anymore. Actually, we'll just comment out the kitten call. And so now we just have this. We're printing the ID of these two variables, right? And if I change y equals 3, now they have two different ID numbers. But here's where this gets interesting. If I make x a list, which is mutable, and I change the element of that list, and now I come down here and I print x and I print y, you'll notice that they're still both the same. What I've done here is I've created a list, I've assigned it to x, I've assigned that x equals y, and I changed the element of the list only in y. I did not change it in x. And the value of both of them was changed. So when you assign a mutable, you're actually assigning a reference to the mutable. And I have this side effect that when I change an element of that list in one place, it gets changed in both places because it's really just one object. And functions work exactly the same way. So if I run this, you notice that we have this list, and the list is being printed in kitten as the list with 5, and in main as the list with 5. It's a one-element list. But if down here in kitten I change a sub 0 equals 3, it's changed in both places. So this is not call by value at all. This is actually strictly call by reference. What's being passed is a reference to the object, and you can change the object in the caller from the function. So this is important to understand. An integer is not mutable, so it cannot change. So when you assign a new value to an integer, you're actually assigning an entirely different object to the name. The original integer is not changed. The name simply refers to a new object. Passing a value to a function acts exactly the same way. A reference to the object is passed and it acts exactly like an assignment. So mutable objects may be changed, and those changes will be reflected in the caller. Immutable objects may not be changed. So function arguments in Python act exactly as assignments in Python with all of the quirks of Python's object model. For the most part, things will work as expected, but be careful with lists and other mutable objects. Python functions allow variable length argument lists, like the variadic arguments in C and other languages. Here in Komodo, I've opened a working copy of args.py from chapter 7 of the exercise files. And you'll notice down here in our definition for our function, we have a variable name with an asterisk before it. This is the variable length argument list. And you notice that we can treat it like a sequence. It's actually a tuple. So I check and see if the length is greater than 0. Remember that 0 is false, anything greater than 0 is 1. And if it is, then I print each of the items in the list. Otherwise, I just print meow. And so when I run this, you notice we get the 3 arguments that we had passed it. And if I call without those arguments, we just get meow with a period, just as it is here in this print argument. It's traditional to name your list args, A-R-G-S, and I recommend that you follow that tradition. That way when people are reading your code, it's obvious what you're doing. And of course, you can call this with however many of these you want, and it will print however many you want. It can be just one, or it can be many. This feature is useful for situations where you want a function that may be called with different numbers of arguments. You may also call the same function with a prepared list like this. And so if I copy this, that'll give us a tuple. And so if we have a tuple or a list or some other collection, I can call it by putting an asterisk before the variable name, and we'll run it and it gets exactly the same results. That'll simply pass a reference to the same object. List arguments are simple to use. They're useful when you need a function that may have different numbers of arguments, and we'll see many examples of this throughout the course. Keyword arguments are like list arguments that are dictionaries instead of tuples. This allows your function to have a variable number of named arguments. Here in Komodo, I've opened a working copy of kwrgs.py from chapter 7 of the exercise files. And you notice down here on line 7, the function argument has 2 asterisks in front of it instead of 1 as we had for the list arguments. And it's named kwrgs, which stands for keyword arguments. And so when I run this, you'll notice that it says kitten Buffy says meow, Zilla says grr, Angel says rar. When we call the function, we have named each of the arguments. Buffy equals meow, Zilla equals grr, Angel equals rar. This is the same syntax as we use for a dictionary, and in fact, this is a dictionary. If I wanted to, I can say x equals and dictionary with those arguments, and then I can pass it x, and just as I would use 1 asterisk for a list, I use 2 asterisks for passing it this dictionary, and our result is exactly the same. Again, it's traditional to name your keyword argument kwrgs. You're not required to follow this convention, but it's generally a good idea to follow a convention so that when people read your code, they'll know exactly what it means. Keyword arguments are powerful and simple. They're useful when you need a function that may have different numbers of named arguments, and you'll see many examples later in this course. In Python, there is no distinction between a function and a procedure. All functions return a value. Here in Komodo, I've opened a working copy of function.py from chapter 7 of the exercise files, and I'm going to come down here and I'm going to assign the return value from kitten to a variable, and then I'm going to print that along with its type. And so when I save and run this, you notice that the type is the none type and the value is none. And that's because if there's no return statement or an empty return statement, a function returns none. If I give it a return statement and say return a number, then we save and run, and now the type is int and the number is returned. Likewise, I can return a list and save and run, and I get a list, or I can return a dictionary. And when I save and run, we get that dictionary. So because of Python's effective object model, Python functions are capable of returning simple or complex values. We'll see many examples of this as we go through this course. A generator is a special class of function that serves as an iterator. Instead of returning a single value, a generator returns a stream of values. Here in Komodo, I've opened a working copy of generator.py from chapter 7 of the exercise files. And first I want to show you the problem that this generator is solving. If instead of calling my function, I call range here and save and run, you notice I've specified the number 25, and in our result, it counts from 0 to 24, which is 25 values starting at 0. I find that a little bit confusing myself at times, and so I created a version of range that I call inclusive range, and it simply works exactly like range, only it returns all of the values from 0 all the way up to 25. So when I save and run this, you see that my result now includes the 25. You're welcome to use whichever version of this you like, but it's great as an illustration of how a generator works, because that's what range is it's a generator. So let's take a look at the generator function. So you notice that we're going to be using a number of the techniques we've been learning so far. First off, you'll notice that we use a variable argument list, and our number of args is the length, and we initialize a couple of variables, and then we use this chain of elifs, if and elifs, to decide how to initialize our variables, however many arguments we get. You remember that range works if it's just one argument, that argument is the stop. If it has 2 arguments, the 2 arguments are start and stop. And if it has 3 arguments, the arguments are start, stop, and step. And if I have less than 1 argument, I raise an error. And if I have more than 3 arguments, I raise an error. And then the actual generator is down here at the bottom. We use a while loop, and we initialize I at the beginning, and while I is less than or equal to stop, then we have this yield. Now yield is like return, except it's for a generator. It yields a value, and then after it yields the value, the function continues until it yields the next value. And so when we run this, we get this result. And you notice that it works exactly like range. I can tell it to start at 5 instead of starting at 0. And when I run this, you notice it starts at 5. And I can tell it to step by 5 if I like. And when I run this, you notice it counts by 5, 5, 10, 15, 20, and 25. I find this a little more intuitive. You may find it different, but it's great as an example of how a generator works. It's really very simple. Most of the processing in this function is dealing with the arguments. The generator itself is really just this 4 lines of code. You notice also that I'm using exceptions for my errors, and we'll talk about exceptions in a later chapter. But if I give it no arguments, I get an error that says type error, expected at least 1 argument, got 0. And if I give it too many arguments, it says type error, expected at most 3 arguments, got 4. And those are these exceptions right here, raise, type error, raise, type error. And if I put this back, it works as expected. So a generator is a special case of a function that is useful for creating a series of values. A decorator is a form of meta-programming, and it can be described as a special type of function that returns a wrapper function. Here in Komodo, I've opened a working copy of hello.py from Chapter 7 of the exercise files. First, it's important to realize that in Python, everything is an object. So a function is a type of object. So if I'm here and I define a function, and I run it, so I'm calling the function, and you notice that it prints out this is f1. But what's interesting here is I can say x equals f1 without the parentheses, and now I'm assigning that function object to the variable x, but everything is an object, so that variable is an object too, and I can simply call the function f1 by calling x. So when I save and run, I get exactly the same result. So this means that I can do silly things like this. So now what I've done is I've created a function f1 that contains another function f2. And I cannot call f2 directly because its scope is inside the function. Remember, functions do define scope. Blocks don't define scope. Functions do. And so when I run this, you notice it runs f2 because the return value from f1 is the object f2. And so I take that return value, I assign it to x, and I call x as if it were a function. I cannot call f2 directly. If I try this, I get a syntax error. Name error. f2 is not defined because f2 only exists inside the scope of f1. So f1 can be said to be a wrapper for f2. Now we're going to create a decorator because this is where this gets actually very interesting. I'll define f3 down here outside of the scope of the function, and I print this is f3. Now f1 is going to take an argument which it's going to use as a function, and I'm going to print this is before the function call, and this is after the function call, and we're going to call f, which is the function that we've passed in the argument list. And now down here, I'm going to call f1 with f3 as an argument, but I'm going to take the return value and I'm going to call on that return value. Now you remember the return value is f2, which calls the argument that's passed in. Now when I run this, you notice we get this before the function call, then it calls F3 because it was passed. But here's where it becomes a decorator. If I assign this to F3 and then call F3, now F3 in its original form is no longer available. Only the wrapper is available. And when I run this, you see it's the wrapper. Because this is so meta and self-referential and weird and recursive, instead there's a shortcut for it, which simply looks like this. Now when I call F3, we get that result. So it takes F3, this syntax here, which is called a decorator, it takes the function which is defined directly after it. So the syntax is you have to have the decorator followed directly by the function definition. And it takes that function and it passes it as an argument to the decorator function, and it returns and it assigns that name of F3 to the wrapper itself. And so now I can't call F3 directly. I can only call it through the wrapper, and F3 now is wrapped inside that decorator function. So how is this useful? Because it's awful meta and weird looking, right? Well, here's how it's useful. Here's a working copy of decorator.py from chapter 7 of the exercise files. I'm just going to drop this bottom pane here so that you can see what it is. I have a function called elapsed time, which wraps the past function in 2 timestamps and prints out the elapsed time. It runs the function and prints out the elapsed time. I have this function here called big sum that adds up a whole lot of numbers together and prints the sum. And then down here I simply call big sum, but because big sum has this decorator, it's actually wrapped in the elapsed time wrapper. And so I'll save this and I'll run it, and you see there's the result. Big sum is that big number, and it took 1.43 milliseconds to calculate that. So that's one practical example of what a decorator is good for. Python provides a number of collection types useful for creating structured data. The list type is a basic sequence. It's created using a pair of square brackets around a list of values separated by commas. The list is mutable, which means that you may add, delete, and change values. A tuple is like a list, but it's immutable. You cannot change it once it's been created. A tuple is created using parentheses. A dictionary is a sequence of key value pairs. In other languages, this may be called an associative array or a hashed array. A dictionary is created using curly brackets. A set is an unordered list of unique values. It's useful for finding and operating upon unique values within a sequence. A set is indicated with curly brackets. Any of these collection types may contain any object or type. As we will see in the rest of the chapter, they may be used to represent simple or complex structured data. The basic sequential types in Python are lists and tuples. Lists are mutable and tuples are not. Here in Komodo, I've opened a working copy of lists.py from chapter 8 of the exercise files. And here we define a list. You notice that the square brackets are used to create the list. A list is an ordered collection, it's sequential, and it's iterable. And you'll notice down here in our print list function, we're iterating with the for loop. So when I run this, it lists in order each of the elements in the list: rock, paper, scissors, lizard, Spock. I can access an individual item in the list using an index. So I can say print game sub1 like this. And if I run that, you'll see we get paper. Lists are zero-based, so item number 0 would be rock, item number 1 would be paper. So the first number is the beginning of the slice, and the second number is the end of the slice, non-inclusive. So in other words, this would be items number 1 and 2, so this would be paper and scissors. And if I run this, see we get paper and scissors. And again, just like range, I can use the beginning, the end, and a step. And so this would start at paper, and it would be every second item, ending at the 5th item. And so if I run this, I'll get just paper and lizard. I can search a list using the index method. So I can say I equals game.index and search for paper. And this will return the index, which I can then use as a subscript. So I can say print game sub I like this. And when I run it, you see that it returns paper. A list is mutable, which means I can change it. I can append an item like this. Run that, and you see we now have rock, paper, scissors, lizard, Spock, computer. Or I can insert an item at a particular index. So I'll insert this, and I'll insert it at 0 at the beginning. And you see computer is now at the beginning of the list. I can remove an item by value. I no longer need that line, do I? And now paper will be omitted from the list, rock, scissors, lizard, Spock. Or I can use pop to remove an item from the end of the list. And this will remove an item from the end of the list. Pop also returns the removed value. And so this is useful with append to simulate a stack. I can also use pop to remove an item at a particular index. So if I remove item 3, that would remove lizard. I can use the delete statement to remove an item by index. Again, that will remove lizard, so we'll get the same result. Or I can remove by a slice. And so that will remove paper and scissors. Or I can remove by a slice like this, and that would remove paper and lizard. I can join a list using the join method on the string type. So I can say print with a string that'll be used to join, and then I can say join and our list. And now it prints out this list joined by comma space in between each of the elements. So that's really useful. I can get a raw count of the items in the list using the length function. And this is a function, it is not an object method, so I can say print len of game, and that will print 5, which is the length of our list. Now, a tuple works exactly like a list, except that it's immutable, and it's indicated by parentheses. So when I run this, you can see it runs exactly the same, but if I try to append, I'll get an error that says tuple object has no attribute append, because tuples are immutable and they cannot be changed. Lists and tuples are fundamental sequence types in Python. The list type is mutable and the tuple is not. I tend to favor the tuple unless I absolutely require a mutable sequence. Python's dictionary type is a hashed key-value structure. This is comparable to associative arrays in other languages. Here in Komodo, I've opened a working copy of DICT dictionary.py from chapter 8 of the exercise files. And you notice that the dictionary is created using curly braces. So there's the open curly brace and the closed curly brace. And there's key value pairs. So that's a key value pair. Each of the key value pairs has a key on the left, a value on the right, and they're separated by a colon. And the pairs are separated by commas within the structure. So that's one key value pair, that's another one, etc. You notice also that I have a little printDict function which prints the dictionary, and when I run it, you can see it prints it in a nice readable format. You can also create a dictionary using the dictionary constructor and keyword arguments. And personally, I find this a lot more convenient, and that looks like this. You can see this is a little bit easier to read, and it's a lot easier to type, and when we save and run, it gives us exactly the same results. Keys and values may be any type. Keys must be immutable. Strings and numbers can always be keys. And this keyword argument method of creating the dictionary is obviously most convenient when you're using strings for your keys. The items method returns a view of key value pairs. This can be used to simplify the loop. So I can say print, or rather for, we'll start with the for loop, for k comma v in, so k and v are the key and value in animals dot items, and I print, we'll use an F string here, and we'll have the key and the value like that. And when I save and run this, I'll just comment out this here. And when I save and run it, you see we get exactly the same result. So I can easily replace this here and say O. And this is a bit more readable. And we can use that for our print dict. And I still get the same result. The keys method returns a view of dictionary keys, so I can say for k in animals dot keys print k, and that we have to scroll up to be able to see that. So why don't I just comment this out here, and now we have a view of just the keys, or I can say I can just get the values like this with the values method, and that'll give us just a list of the values. A dictionary is indexed by its keys, so you can easily pick a particular element. You can say print animals sub lion, and that will just print the lion. It's just the value. So the subscript returns a value just like it does with a list, only in this case you're using the key instead of an index. In fact, you may use this to assign a different value to the lion. You can have it say, I am a lion. And now when we print it, we get lion is I am a lion. Or you may add a new item. Say monkey. And monkeys, of course, say ha ha. And when I run this, I now have monkey at the end of my list. You can search for a key by using the in operator. So say lion in animals, and you'll notice that that returns a true value. You see that at the top of the list there, true. Or you can use that with any conditional expression. And so that'll say found. And if I'm looking for something that's not there, you see it says nope. If you try to access a key that doesn't exist, you'll get a key error exception. So if I say print animals sub Godzilla, you notice that I get an exception, a key error Godzilla, because that key does not exist. Or you can use the get method to return a value when you don't know if the key exists. So I can instead say animals.get like that, and I get the none value because that key doesn't exist. So that if you don't want the exception, if you want just a none value, you can use the get method. So Python's dictionary type is both simple and useful. You'll see many examples in the rest of this course. Python has a data type for sets. A set is like a list that does not allow duplicate elements. Here in Komodo, I've opened a working copy of sets.py from chapter 8 of the exercise files. And you'll notice down here on line 5 and 6, I've defined two different sets. And I've defined them just using strings. And when I run this, you'll notice using my print set function below that what I get is an unordered list of the unique characters in each string. There's no duplicates because a set does not allow duplicates. And the lists are unordered. Each time I run it, you'll notice they come up in a different order. Of course, it's entirely possible to sort them if you really want them in order. And now you see that they are both sorted, and each time I run it, they come up in the same sorted order. But mostly, if you're using sets, you're going to be checking the membership of the set and using them as sets, not as lists. If you want an ordered list, you'll use a list or a string. So for example, I can check for the members that are in set A but not in set B by using the minus operator. And that's the members of set A that are not also in set B. I can find the members that are in set A or set B or both by using the vertical bar operator, and that's all of the members that are in one or both of the sets. Or I can look for the exclusive OR using the caret operator. So that's A or B but not both, and when I save and run that, I get an entirely different list. Or I can look for only the members that are in both, and when I save and run that, you see we get that different list. So like the other collections in Python, members of a set can be any type. In this case, I found that the strings were a convenient way to get a bunch of data into them easily so we can look at the intersections of the sets. And a set is like a list that does not allow duplicate elements, and it's a useful tool in many circumstances. A list comprehension is a list created based on another list or iterator. Here in Komodo, I've opened a working copy of comprehension.py from chapter 8 of the exercise files. List comprehension is a very common technique in Python, so it's good to understand it. Here on line 5, I've created a sequence based on the range function, the range generator, so it'll be 0 to 10. If I save and run this, you'll see it says 0 through 10 in our output. We have this little print list, which is for printing our sequence. And let's go ahead and create a list comprehension. I'll create a second sequence. I'll call it sequence 2. And this one will be a list. And it'll be a list of each of the elements of our first list multiplied by 2. So I'll just say x times 2 for x in sequence. It's as simple as that. And when I go ahead and print this with our print list, you'll see that it prints each of the elements of the first list multiplied by 2. So we now have a separate sequence, which is the first sequence multiplied by 2. We can do a lot of things with this. We can get a list of all the elements of our first list that are not divided by 3 by saying x for x in sequence if x modulo 3 is not equal to 0. And now I'll run it, and you see we get only the elements that are not divisible by 3. You'll notice I have this extra if clause, and that's allowed only after the for clause. I can also create a list of tuples if I want to, x comma x squared. So this will be a list of each element of our sequence squared and the element squared. So there'll be 2 in each element here. There'll be a tuple for x in sequence. And when I run it, you see we get a list of tuples with the original element from the sequence and the squared element. You can call functions if you want to. Here I'm going to import from math. Oh, I don't need the import there. From math, import pi, so I have this constant. And our sequence 2 is now calls the function round pi I for I in sequence. And so now I'll have pi rounded to the number of places for each element in the sequence. So pi rounded to 0, pi rounded to 1, pi rounded to 2, 3, 4, 5, etc. You can even create a dictionary. And so I'm going to create a dictionary here instead of a list. I'll say x squared for x in sequence. And for this, I'm not going to be able to use my print list. I'll just say print. And there's our dictionary. For each element, we have the key, which is the original element for our sequence, and its square. And you may also create a set. I can say X for X in SuperDuper, a little string there, if X not in P and D, like that, and that'll give me a set, and I can use print list for this. This is fun. That'll give me a set of all the letters in the string SuperDuper that are not also in the string P and D. So everything that's not a P or a D in SuperDuper. This is a little bit surprising because a set is, of course, just the unique members. And so when I run it, there's just 4 letters there that are not P or D in SuperDuper. So list comprehension is a powerful technique for creating lists and other collections. You'll see it often in Python code, and you'll see other examples here in our course as well. In Python, everything is an object, and variables store references to objects. This means that it's possible to store anything in a data structure. Here in Komodo, I've opened a working copy of mixed.py from chapter 8 of the exercise files. And you notice here in my main function, I have a rather complicated set of stuff. I have R is a range, L is a list, and that list includes integers, strings, a dictionary, and all kinds of stuff. T is a tuple, which again includes strings and a none value in the middle of it. S is a set. D is a dictionary. And then I have this mixed, which is a list of all of these different structures. And then I have this display function, which I'll show you in a minute, which will display the mixed. And I'm just going to run it right now. And you can see down here, here's all our different elements. So first is the list. And you remember the list has 1, 2, and it's got a dictionary in the middle of it. Then is the range. Then I have the set. And so that's all of the characters in the set. Then I have the dictionary, and see the dictionary has 1 is R, which is the range, 2 is L, which is the list, 3 is S, which is the set. So we have all this stuff in that dictionary there. And then we have the tuple with the 1, 2, none, which is displaying as nada because of the way that I have my display functions set up. So let's take a look at the display function. You can see that this is a really interesting data structure. And what I've done is I've used isInstance to determine, is it a list, is it a range, is it a tuple, is it a set? And I have different print functions for each of those. And you notice this function is called display, and each of these print list, print tuple, they each call display for the elements within it. And so it can test and see if it has to print another structure, or if it's none, it's going to print the word nada, or otherwise, if it's none of those things, it's just going to print a representation. I also have this global variable here, dLevel, to keep track of my nesting level so that when I get to an outer level, I can print a new line. And so when I run it, this is the result that we get. You can see that our structures can be as complex as we want them to be, and it's possible to iterate through these structures and introspect each element of each of these structures and decide what to do with it. And so I just wanted to show you this. I know it's kind of complex, but this is the power of Python's object model. Everything is an object. Objects may contain references to other objects, including your own defined classes and objects, and we'll get to that in a later chapter. And this allows you to create virtually any structured data. A class is the basis of all data in Python. Everything is an object in Python, and a class is how an object is defined. Here in Komodo, I've opened a working copy of class.py from chapter 9 of the exercise files. And down here, beginning on line 4, we see our class definition, beginning with the keyword class, and the name of the class, and a colon, and then everything that defines the class is indented under that declaration. We have data in the form of these variables, And we have methods in the form of these function definitions. You notice that the first parameter of a method is always self. Self is not a keyword. You can actually name that first parameter whatever you want to, but self is traditional, and I highly recommend that you use self so that as people are reading your code, they know what you're talking about. So the first argument is self, which is a reference to the object, not the class, to the object. And so when an object is created from the class, self will reference that object. And then everything that references anything defined in the class is dereferenced off of self to get the instantiated object version of it. And the period operator is used to dereference the object. And the same is true outside of the class. So here we've defined a variable, Donald, from the class duck. And then in line 16, we invoke the object method, quack, on the object Donald. And so Donald is the object because it was instantiated from the class. The dot operator dereferences the object so that you can get to the method, in this case, quack. And so quack and move, as you can see, they print the sound and movement variables from up here. And so when I save this and run it, we get those two strings printed. In fact, if you wanted to, although it's not recommended, you could simply print Donald.sound, the variable itself, and get exactly the same result. So this is the basics of how a class is defined. We'll cover many more details about classes and objects in the rest of this chapter. An instance of a class is called an object. It's created by calling the class itself as if it were a function. Here in Komodo, I've opened a working copy of constructor.py from chapter 9 of the exercise files. And I'm going to close this bottom pane for a moment. And if we come down here to the bottom, you see down here in main, I create two objects, A0 and A1, from the animal class. And I'm initializing it with various parameters: type of the animal, the name of the animal, and the sound that it makes. I'm also simply calling printAnimal. So printAnimal is this function here that expects an animal object and prints the animal. And I'm calling it directly here from the constructor, from the class, without creating an intermediary object. This works exactly the same way because if you'll remember, function parameters work exactly like assignments in Python. And so when I run this, you see I get three animals: a kitten named Fluffy that says rawr. And if we scroll down here, you can see that. A duck named Donald that says quack, and a velociraptor named Veronica that says hello. So let's take a look at the class constructor. There's a special class method name called init with double underscores before and after. So those are two underscore characters, 1 and 2, both before and after the word init. And that's a special name for a class function which operates as an initializer or a constructor. And so you pass it three arguments. Of course, the first argument is always self, and that's what makes it a method, an object method, because this self points at the object. And then the three parameters, type, name, and sound. And those are used to initialize object variables. And these are object variables because they're never initialized until after the object is defined. So they don't exist in the class without having been constructed into an object. And you notice that the object variables all have an underscore at the beginning of the name. Again, this is traditional, and this discourages users of the object from accessing these variables directly. Instead, you have these accessors or getters. I call them getters, some people call them accessors, which simply return the value of those object variables. And then down here, when we print the animal, we use those getters in order to access the variables. So the object is created by using the class name as if it were a function name. And this calls the constructor. Now you'll notice that I have these three parameters. I don't have any easy way of really remembering the order of them. So a lot of times instead, somebody will do it this way. We'll use kwargs. And then each of these can be kwargs subtype and name and then down here I can say type equals kitten, name equals fluffy, and sound equals rar. I'll go ahead and do this without the extra spaces around the equal sign and do the same thing here. And here. And now when I run it, of course, I have exactly the same result. But now it's a little bit easier to remember these parameters, and I can put them in any order if I want to. In fact, I can even give them default values. I can say if type in kwargs, else, and give it a default value. And now if I want to, I can come down here and I can say print animal and just give it the animal class with simply parentheses, which will give it the default object. And now when I save and run it, you see we get the last one here, which is a kitten named Fluffy that says rar. So that's just a little bit about the constructor. An object is an instance of a class. An object is created by calling the class as if it were a function, and the constructor is used to initialize the object. A function that is associated with a class is called a method. This provides the interface to the class and its objects. Here in Komodo, I've opened a working copy of methods.py from chapter 9 of the exercise files. And if we look down here, we'll find this method called type, which serves as both a getter and a setter, and so I call it a getter-setter. You'll notice that the first argument to the function is self, and that's what makes this a method and not just a plain function. This is filled in automatically. When I call this method on the object, I don't provide this argument. So I'll just provide one argument, and the fact that it's being called on the method will provide the first argument, self. It's common to name this argument self, although it's not required. You can name it whatever you like. But it's a really good idea to always use the word self because it's traditional, and when people are reading your code, they'll know what it means. So in this case, the second argument is t, and you notice it has a default value of none. So if there is no value, or if it's none, then this if will fail and it'll just return the value of type. If there is a value, then it'll go ahead and it'll set type before returning it. So that's what makes it a setter-getter. You'll also notice that the object variables are named with a leading underscore, and this again is traditional. Python doesn't have private variables, and so there's no way to actually prevent somebody from using these, but this indicates that it's a private variable and that should not be set or retrieved outside of the setter-getter. So when we run this, you'll notice that we have the same output as we did in previous lessons. And if I go down here to the bottom, you'll notice that I'm creating two objects, A0 and A1, for the two animals. And I'm printing them out. And we'll get in a moment to how this is happening, that I'm just printing them out with print directly like that. But if I take, say, A0, and I want to change its sound, I simply call the sound function, and I change it to, say, a bark. And now, when I run this, you notice that Fluffy says bark instead of rar like it was initialized to. And that's because I have set this variable using the setter-getter for sound, which is right there actually at the bottom. Now you'll also notice this special method called str with two underscores before and two underscores after. We've seen this before. in our constructor init with 2 underscores before and 2 underscores after. So this is a specially named method which provides the string representation of the object. And this allows us to print it with simply this print and the object like that, without needing a special function like we had in previous lessons. You can find a list of all the special method names here in the documentation under Data Model, and if you click on Special Method Names, you'll see a whole bunch of them with all of their descriptions. And there's str right there, the informal or nicely printable string representation of an object. And there's just a lot more of them. There's all the comparison operators, and this list goes on for quite a while. Methods are the primary interface for classes and objects. They work exactly like functions, except they're bound to the object through their first argument, commonly named self. Data may be associated with a class or an object, and it's important to understand the distinction. Here in Komodo, I've opened a working copy of variables.py from chapter 9 of the exercise files. And here in the init method, which is our constructor, you'll notice that I'm initializing 3 different variables, type, name, and sound. And these are object variables. They only exist when the object is created from the class. They do not exist in the class itself. And so I'm going to go ahead and run this, and you can see we're using those variables. But what's important to realize here is that if I come in and I change one of them, A0 name equals Joe. Now, this is not a good idea, and you don't normally want to access these underscore variables directly. The underscore means don't do that. And so I'm just doing this for demonstration purposes so that we can see that when I print A0.name, I'm going to move this stuff to the end here. Oops. I copied it, I didn't move it. There we go. So you see that A0 name is Joe, and A1 name did not get affected. A1 name is still Donald. So these are object variables. They don't exist in the class, and they're bound to the object, not to the class itself. Now, if instead I come up here and I create something mutable so we can actually demonstrate this, I'm going to create a list, 1, 2, 3. This is a class variable, not an object variable, because it's defined in the class. It's not defined in any method. And so if I come down here now and I print A0.x, then you see I have that list, 1, 2, 3. If I now change in A1, not in A0, in A1, the first element of that list to a 7, let's say, and then I'll print it again, you'll see that I've changed the value, but I'm printing from A0 and I changed it in A1. That's because this variable is associated with the class and it only exists in the class. The object actually doesn't have this. It's drawing it from the class, not from the object. And that's a very important distinction. So this comes to something called encapsulation. Encapsulation is one of the major benefits of object-oriented programming. If my variables are encapsulated, that means that they belong to the object and not to the class. This variable here, this x variable, is not encapsulated. And so it exists, it's exactly the same object in every instance of the class, in every object that's created by the class, because it only exists in the class. So that makes it not encapsulated. As a general rule, except for things like constants that you're never going to change, and those should be immutable, not mutable, you're really never going to want to put mutable data in the class. That's generally speaking a very bad idea. So I'm going to go ahead and remove that now, and our class is back to normal. And I just want to talk a little bit more about these setters and getters. Again, this is one of the principles of encapsulation, is that you never want to access these variables directly. and that's why they have the underscore in front of them. In many languages, there's a concept of private variables that simply cannot be accessed or changed from outside of the class definition. Python doesn't have that. Instead, we have a convention, and the convention is to use this underscore, and that means do not touch this. And so you never want to set that directly from outside of the class methods. And so here I have this method which sets it and gets it. It's set in the constructor here. And even when I read it in my string function, I'm reading it using the getter because that's just safe. And so it's important to understand and to adhere to this convention of never setting or getting these object variables directly, to always use a method to do that. So it's important to understand the distinction between class variables and object variables and how to properly encapsulate data in your objects. Class inheritance is a fundamental part of object-oriented programming. This allows you to extend your classes by deriving properties and methods from parent classes. Here in Komodo, I've opened a working copy of inheritance.py from chapter 9 of the exercise files. And you'll notice in our init method, we're no longer providing any default values. And that's because this is now just a base class and it's going to be inherited in order to be used. Because of that, now we need to do a little bit of extra checking in our setter getters. We can't just return a value. We need to check and see if the value is actually there. And so I'm using exceptions for this. This is the normal way to do this. We're going to cover exceptions in a later chapter, but just understand that what this does is it attempts to return the value, and if that fails, it returns none instead. So to actually use this class, we're now inheriting it to create other classes. We've got a duck class and a kitten class. And in each of these cases, we set the type to, in this case, duck, and we check and we see if there is a type in the keyword arguments, and if so, we delete that. And then through the super function, we call the parent class initializer with our KW-args. So super always calls the parent class. And then down here, we initialize A0 with a kitten and A1 with a duck. And when I run this, you notice we get the result that we expect. So this allows me to do things like a special case. For example, here in kitten, we can define a method that doesn't exist in any of the other subclasses of animal. And so in this case, we'll call this one kill, because we know that kittens are actually predators and they're always trying to kill something, right? And again, we start with self and S. S will be the string that will identify the target of its predation. I don't know if that's a word or not, the target of its killing. And we'll use print and we'll use an F string, self.name will now kill all, and the string, exclamation point, because that's a pretty important thing to know. And then down here, I can simply say print A0 is the kitten, and actually I don't need a print because I have a print in my method there. I can just say A0 dot kill humans. And now when I run it, Fluffy will now kill all humans. But I cannot run that on A1 because I get an attribute error. Duck object has no attribute kill, because that only exists in the kitten and not in the duck. So you can also, of course, extend built-in classes, because in Python, everything is an object. Here's an example here. I have a working copy of string.py, also from chapter 9 of the exercise files. And here you'll see that I'm inheriting from str, and it does not have a capital first letter. This is a built-in class built in to Python, and that's our standard string class. And I'm inheriting from that, and I'm overriding the string representation method to, instead of returning the string itself, to return a slice of the string where the step goes backwards. And so this will reverse the string. So this is a type of a string that every time I print it, it'll print backwards. And here I create one with hello world and I print it. And when I print it, you'll notice that it prints hello world backwards. So you can see that class inheritance is a very powerful thing to be able to do. And you can inherit and extend and even, as in this case, change built-in classes or classes that you define yourself. Class inheritance is a vital part of object-oriented programming, and in Python, you can see it's relatively easy and intuitive. An iterator is a class that provides a sequence of items generally used in a loop. Here in Komodo, I've opened a working copy of iterator.py from Chapter 9 of the exercise files. This is an iterator class implementation of the inclusive range application. It's functionally identical to the generator from the functions chapter. So let's take a look at how this works. Here we have our constructor, and our constructor simply sets up all of the variables and it checks the arguments. It checks how many arguments we have. If there's just one, that's the stop. If there's two, it's start and stop. And if there's three arguments, it's start, stop, and step, just like the range function, the built-in range function. And if we have the wrong number of arguments, we get a type error exception. Again, we'll cover exceptions in detail later on in this course. And we initialize the starting point of our iterator. And then we have this special iterator method, ITER, with the double underscores on either side of it. And this simply identifies this object as an iterator object. And then there's the next function, which is the iteration itself. A construct like the for loop is going to look for this next function in order to treat this as an iterator. And in order to use it for iteration, if we've reached stop, we raise the stop iteration exception. Otherwise, we go ahead and increment and return the value. And you'll notice there's no yield here. Yield was implemented later than iterators, and generator functions are actually a simpler way to do exactly the same thing, but iterators are still very common. And so here we have our application for n in inclusive range, and we use this just like we would with range. And so when I run this, you see we get our range, and come down here to the end again. You can see we've passed it a 25, and so we get 0 through 25, including the 25. And if we use this with just the built-in range function, you notice that we get that without it's not inclusive. It doesn't include the 25. I can set this up to start someplace else. So I can say start at 5, and when I run this, it's 5 through 25. And I can tell it to step by 5, and when I run this, you notice it steps by 5 instead of by 1. Or I can use some other number here. I can have it step by 3 or whatever. So an iterator is functionally identical to a generator function. A generator function is often easier to implement and will work just as well, but it's good to understand how iterators work, and you'll certainly see them in the wild. Exceptions are a powerful runtime error reporting mechanism commonly used in object-oriented systems. Here in Komodo, I've opened a working copy of hello.py from Chapter 10 of the exercise files. And what I'd like to do here is just generate an error. We'll say x equals int of, and we'll give it a string. And so that's an error. And when I run this, you see we get this error message down here. I'm going to just expand this a little bit. And there's a lot of stuff here. At the very bottom, you'll see it says value error, invalid literal for int with base 10, foo. So that's our actual error message. Everything else is what's called traceback. And you can see it says traceback, and it goes bottom to top. So the actual line with the error is on line 5. And you see that my cursor up here is on line 5. And that's where the error is. Line 7 is where that is called from. And so down here on line 7 is the main call, which calls the function that has the error. So this traceback, under some circumstances, could help you to trace where the error is or what caused the error. But for our purposes, we're looking at the error itself, the exception error, and you see that it says value error. Value error is a token. It's the name of the type of an error that is being generated here. And so what I can do is I can catch that by catching the exception. You do this with the try command, or the try statement rather, and you can put whatever you want in the try block. Get my cursor out of here. And then I say except, and this is what will be executed if the try fails, if it generates an exception. And I can catch a specific exception by saying value error. And you notice there that I get a list of the possible exceptions, and there's a lot of them. But we know this is value error because we see it in the error message down there. And so what am I going to do if I catch a value error? I'm going to say print, I caught a value error. And I save and run this, and now instead of getting that whole error message, I have captured the error. The other nice thing about this is that by capturing the error, I can handle it intelligently, and I can go on with my code. I can actually do something else because I know that this didn't work. So I could assign a rational value to X, or I could call a function or whatever. But I've caught that error, and now my execution continues. If I don't catch the error, then it actually stops the execution of my script. So there's a number of different possible errors here. I can say X equals 5/0. I'm dividing by 0, which is generally going to cause an error. So I have a zero division error. I can actually capture several different types of errors in the same try block. Zero division error, print, don't divide by 0. And you notice that I have this single quote there. I can escape that with a backslash. And now when I run it, it'll say don't divide by 0. So I can do this as many times as I want to, all in the same try block, to catch different types of errors. And if it succeeds, I can use else. And this will only be executed if I don't have an error. And print, good job. And I can divide this by 3 instead of by 0. And I can actually print the value here too, if I want to. And now it says good job, and there's 5 divided by 3. But let's say that I have an error that I wasn't expecting. So maybe I'm not expecting the zero division error. I can have a default except that does not know which error it is, and I can say unknown error. And I did that, okay. And so now if I'm dividing by 0, I get this unknown error, but I can still continue because I caught the exception. If I want to know more about the error, I can import sys, which has a lot of constants in it that'll help me to understand things like this. And I can make this an F string, and I can say sys.execInfo, and that'll give me more information about the error. I can run it. Yeah, I misspelled it. It's like that. And now it tells me more about the error, or if I want to, I can actually subscript from that and get the specific error. And save and run, and it says unknown error, division by 0. So Python has a rich and complete system for handling exceptions. You can also generate your own exceptions, and we'll look into how to do that in the next lesson. Exceptions are an excellent way to report runtime errors. You can generate your own exceptions for error reporting in your code, and this is considered best practice. Here in Komodo, I've opened a working copy of exceptions.py from chapter 10 of the exercise files, and you'll notice, if you've been following along in order, that this is our inclusive range example from the functions chapter. And here, in the initializing parameters section, if I have the wrong number of arguments, either less than 1 or more than 3, Then I generate an exception using the raise statement. So I raise and I give the error the exception class. In this case, it's type error, which is recommended for this type of an error. And down here, when I run it, I have the correct number of arguments here. So if I run this, you see I get the result I expect. But if I have no arguments, I get this exception. It says type error. And you notice I have a whole trace back here, exactly as we would expect. Or if I give it too many arguments and run that, I get the message that I have too many arguments. Now, of course, I can catch this just like I would with any exception by using try. And I'll put all of this in the try block. And then I say except. And this is a type error. I can say as E to get the error message. And then I can print range error and the message. And now when I run it, I get range error, expected at most 3 arguments, etc. So this is working exactly as I expected. Exceptions are a convenient and useful way to report errors from your own functions and classes. Strings are first-class objects in Python 3. This is different than many other languages, and it's even a little bit different than Python 2. Even though strings were objects in Python 2, they weren't fully first-class objects, and the string interface is far more consistent now. But change is still change, so if you're familiar with Python 2 strings, you'll want to pay close attention here. Here in Komodo, I've opened a working copy of hello.py from chapter 11 of the exercise files. And let's start taking a look at a string as an object. Here we have a literal string, and even though it's a literal string, I can still call methods on it. So I can call the upper method, and when I run this, we get hello world in all capital letters. Or I can run the swap case method, and it'll simply swap the case. If it was capital in the original string, it'll make it lowercase in the output string. In fact, it's so common to call methods on a literal string in Python 3. String formatting is commonly done like this. And I'll put in a placeholder here. And when I run this, I get the result 294. And all of this works with single, double, or even the triple quoted strings that are unique to Python. And this is actually usually done with double quotes, although it works with either. And I can just put things on different lines. I can put spaces between things. And when I run this, it has it all formatted like that. So all of this works because strings are first-class objects in Python. Of course, all of this applies as well to a string as a variable. And so if I simply assign a variable and print, I can put the format on the variable, and it still works exactly as we expect. In fact, you can even subclass strings in Python. So if I say class myString and put the original string class, the string class is called str. That's the built-in string class in Python. And so I can subclass from that. And you'll recognize this if you watch my objects chapter. And I'll just take this out and take out the format, and we just print S like this, and it'll print it backwards. Need to actually make it myString. And it'll print it backwards. So all of this makes strings extremely powerful in Python 3, and we'll get into more detail in the rest of this chapter. The Python string object has a number of useful methods. Here are some common ones. Here in Komodo, I've opened a working copy of hello.py from chapter 11 of the exercise files. And you notice down here on line 4, we have our print hello world. And if I run this, it prints hello world in our results. If I use the upper method on the literal string, You notice it prints in all capital letters. And if I use the lower method, it's in all lowercase. There's also a capitalize method, which capitalizes just the first letter and makes everything else lowercase. There's a title case, which capitalizes the first letter of every word. And there's swap case, which will swap the case of every letter. So the capital letters are lowercase and the lowercase letters are uppercase. There's also case fold. And if I run this, you'll notice it makes everything lowercase. The difference here is that case fold is similar to lower, but it's more aggressive. And it removes all case distinctions, even in Unicode. So if I use like a German sharp S here, and we run this, you'll notice that comes out to a lowercase ss, where if I just do this in lower and run it, you notice it does not lowercase the German sharp S. And so that's useful for words like Straße, the name of a street in German. And if I make that case fold, then it spells it in lowercase. So it's important to note here, let's put this back to uppercase and remove that. It's important to note here that a string is immutable. It cannot be changed. So when you use one of these transformation methods, the return string is a different object. So for example, if I say s equals, and I'll just copy my string with the upper there, and s2, we'll call this one s1, and s2 equals, take this like that, and we'll say s1 dot upper. And now I'll go ahead and I'll print the ID of each of these. You'll notice that they're entirely different objects. So the upper method here in line 5 has not just transformed the string in place, rather it's created a new object and returned that. If you need to concatenate two strings, that is to combine them into a new string, you can use the plus operator. So I'll just make another string here. This is another string. And I can print S1 plus S2, which will concatenate them. Or if I want a space in the middle, I can put a space in there like that and run that. Literal strings can be concatenated like this. And I can print S3. And you see that that is one concatenated string. Python strings are very powerful. For more details, see the Python documentation here. This is at docs.python.org/3/library/standardtypes.html. And if we scroll down here, text sequence type, string methods, you'll see that there's quite a few of them, many more than we could cover in just a few minutes on this video. But that's the full documentation, and you should be able to follow that pretty easily after our introduction here. Python has rich string formatting capabilities. Here in Komodo, I've opened a working copy of hello.py from chapter 11 of the exercise files. Python 3 uses a string method called format to format strings, and it works like this. If I create a variable called x equals 42, and here in the string I can say the number is, and I use these curly braces for a placeholder, and I type format and give format the variable x, and when I run it, you'll notice it says the number is 42. So in some languages they call this string interpolation, but here the method of the madness is exposed by allowing us to use the format method like that. The curly brackets are a placeholder, and the format method specifies values for the placeholder. If you have multiple values, say y is 73, and I want to give another number here, I can specify the second value in format with a comma, and when I run it, you see it displays both numbers. You can name your variables like this, XX and BB, and then in the format you can say XX equals and BB equals. And when I run this, you see our result is the same, or I can change them around. Call this one XX and this one BB, and it'll change them around in the result. Likewise, you can use positional arguments, say 1 and 0. The positional arguments start at 0, so here I'm reversing them again. And when I run this, you see it's still 73 and 42, but if I change them around, now it's 42 and 73 in our result. And this even allows me to repeat a value if I like, and run this. I have 42, 73, and 42. Now, again, without anything specified, it simply takes the arguments in order. And so there's our two arguments. You can also add formatting instructions. Formatting instructions are preceded by a colon. And of course, if you had any positional arguments, you would put that before the colon. So I can say 0 and 1 colon like that. And I can say that I want this one left justified with 5 spaces and this one right justified with 5 spaces. And when I run that, you see we have all kinds of spaces between them. So the number is the number of spaces including the value. And if I want to, I can add a leading 0. And you see now I have 5 positions. 2 of them are taken up by the value and the other 3 are filled with 0. I can add a sign if I want to. And now that'll have a sign, even if it's positive, it'll still give me the sign. And I can use that in combination with the positional argument or even with the leading zeros, and all of that still works. You'll notice that the sign takes up one of the 5 positions. Okay, let's go back to using one value here, and I'm going to call this 42 times 747, because I want to get a nice big number. So when I run this, you notice I have a nice big number. If I want to format that with commas, I simply put in a colon for the formatting instructions and add a comma, and now I have the comma for 1,000 separation. And I can make that a bigger number if I want to, and you notice that it just continues to use the commas properly. And if I'm European and I want to use periods instead of commas, I can always use the replace method and replace the comma with the period. And we run this. Oh, not enough parentheses. There we go. And the number is now formatted with periods instead of commas. You may also specify a fixed number of decimal places with the letter F. So if I run this, you notice it defaults to that many decimal places, or I can say 0.3 and run it again, and now it gives me 3 places to the right of the decimal point. You can specify different bases. I'm going to put this back to the number 42. And we'll print this in hexadecimal, which is 2A, or octal, which is 52, or binary, which is 101010. Beginning with Python version 3.6, you may now use F-strings for formatting. And so this is instead of this whole format thing here. And it looks like that. So I put the letter F, either lowercase or uppercase, but I prefer the lowercase, in front of the string, and then I use the variable name where you would otherwise use the positional argument with the format method. And so when I run this, it's number 42. And if I want to do some formatting, I can say .3f, and it'll give me 3 decimal places. And all the formatting methods that I've already shown you will work with this method as well. In fact, the F string is simply a shortcut for the format method. I tend to prefer the F strings, and I expect that they will quickly become commonplace for Python 3 code. For more details on string formatting in Python, python.org has a full reference here, and click on Format String Syntax. And this is complete documentation. It's a little bit techie language, but it's all there. Python allows you to easily split and join strings based on separator characters. Here's how this works. Here in Komodo, I've opened a working copy of splitjoin.py from chapter 11 of the exercise files, and here we have a string with a bunch of words in it. I can easily split this into a list like this, and when I run this, you see our result is a list with each element as a separate word from the string. So what Python has done here is it's folded all the spaces and then split the string on the spaces and loaded up a list with each of the individual words. And so I can add as many spaces as I want here. In fact, I can even add new lines, and so we'll make this the triple quote, and I'll just add a new line there and one there. And when I run this, you see we get exactly the same result, because what Python has done is taken all those spaces and new lines and it's folded them all together before splitting it. And so this is the default behavior of split. It's how most people usually use it. And of course you can change it. I can say split on the letter I instead. And when I run this, now it's leaving all the spaces alone. Instead, it's splitting on the letter I. And so it removes the I and splits on the I, and then loads up the list with the separated parts of the string that are separated on the I. Now, if we put this back, I can take that string and I can say L equals s.split. And now I have a list that's the split string, and I can say s2 equals, and join it back together with colons instead of spaces. So there's a colon and join, and give join the list. So join is a string method, but the string is the separator that it's going to be joined with. And join takes a list or a tuple as its argument. And now I can print S2. And when I run this, you notice that we have a long string with a bunch of words in it, but instead of spaces, we have colons. We can put whatever we want here. We can have dashes, and I run it and it looks like that. Really, we can use whatever we want. So splitting and joining strings is a common operation. Python's object model makes it relatively simple to do. Python provides the open function for opening files. Here in Komodo, I've opened a working copy of files.py from chapter 12 of the exercise files. And in a nutshell, we open a file and we read the file line by line, stripping the new lines off the end of each line, and display them. So when I run this, you see we have this output here. I'm just going to open this up a little more so we can see the whole file, first line through 10th line. And this is the file here. You notice the file is lines.txt, and I have the original file here, and you can see that we're taking each of those lines and we're displaying them faithfully. So let's take a little bit of a look at how this works. The open function returns a file object. It takes a file name, it opens that file, and it returns a file object. The file object itself is an iterator, and so we can use a for loop and get one line at a time without having to buffer the entire file in memory. And there's a method here you may not have seen on the string. Obviously, each of the lines is returned as a string, and the string class has an rstrip method which will strip any white space, including new lines, from the end of the line. And this allows us to print them or to do whatever with them without having to worry about dealing with the line endings. A little bit about the open function here. By default, it opens the file in read-only mode, which would be the same as providing a mode with a R letter. Open takes an optional second argument, which if it's a simple letter R will open in read mode. If it's a W, it'll open it in write mode. And if you open in write mode, it empties the file if the file is not empty, and it starts at the beginning and writes over the file. If the file doesn't exist, it creates it. A is append mode. This is just like write, but if the file already has some content in it, it starts at the end of the file, and it does not empty the file, and it does not create the file. There's an optional plus which you can use with any of these modes, which will allow you to both read and write. And there's an optional letter B or T, which will specify binary or text mode. And we'll look at the meaning of binary and text mode later in this chapter, but it's worthwhile to know that it defaults in text mode. So here we are in the default read mode, and when I save and run this, you see it reads the file line by line and displays the lines. So the open function is used to open files in Python. It's very simple and very functional. Because of the diversity of computers and operating systems in the world, some systems handle text files differently than others. For example, this is a text string with the word string in it. The English word string has 6 letters. This is followed by a meta character that indicates the end of the line. This is sometimes referred to as the new line character and is generally represented by a backslash and a lowercase n. The history of line endings is long and convoluted. In many systems, it is represented by a single line feed character, ASCII 10 decimal or 0A hex. These systems include most Unix-based systems, including modern Macs. In this case, the string has 7 bytes, including the line feed. In other systems, a new line is represented by a carriage return character, ASCII 13 decimal or 0D hex. These systems are mostly obsolete, including the Apple II and classic Macs, TRS-80 and old Commodore systems. In this case, the string has 7 bytes, including the carriage return. Microsoft Windows machines use a sequence of both carriage return and line feed characters, in that order. Other older systems, including CP/M, OS/2, and old digital equipment mini-computers, use this line ending. In this case, the string has 8 bytes, including the carriage return and the line feed. Because of the need to properly recognize any combination of these line endings, most systems have separate modes for opening text files and non-text or binary files. We will discuss these 2 file modes in the rest of this chapter. Reading and writing text files is remarkably easy in Python. Here in Komodo, I've opened a working copy of copytext.py from chapter 12 of the exercise files. Here we have our input file, which is 10 lines of text, and it's called lines.txt, and so when I use the open function, I'm opening lines.txt. I'm opening it in read mode and in text mode. And of course, this is the default. If I were to simply omit this argument, it would still open in read mode and text mode, but I like to be explicit and remember the Python principle that explicit is always better than implicit. In the next line, I'm opening the output file, and this is called lines-copy.txt. And you notice in our file listing over here on the left, there's lines.txt, but we do not have a lines-copy.txt yet. That'll be created when I open this file in write mode. And again, I'm specifying the T for text mode, even though it is the default. Now our in file is the one that we open for reading, and so I'm using a for loop to read the file. And then for each line in the file, I'm using the rstrip method to strip the line endings from the file. And I'm using the print function with file equals output, and that's our file handle that we opened here on line 6. I also print a dot, and you notice I have this end equals empty string, and that prevents print from printing a new line after each dot, so that they'll just go across the line and make a little progress bar. And this flush equals true. This flushes the output buffer. On some operating systems, the output buffer is flushed, and you may not get any of those dots printed until you print a new line. And I do that down here on line 11. On line 10, I close the out file. And this is important because, again, buffering, all of what we've written to the file may not be completely written by the time our main function ends, and we want to prevent any data loss. So it's a good idea to close the file explicitly that you've written to. You can also close the in file. I could say infile.close. And this is less important because you're not going to really lose any data. And it'll be closed automatically when we exit the main function. So now I'm going to run this. You notice it happens very quickly. You don't see the individual dots. They're being written for each line of the file. But you'll also notice down here that we now have a lines-copy.txt, and if I open that up, it looks exactly like our input file lines.txt. So we have successfully copied our text file. You may optionally, instead of using print to write the file, you may use the outFile method write lines. And this will work just as well when I save and run this. You see we get exactly the same result, and our output file is exactly as we expect. The difference is that with the print function, I'm able to strip these line endings and rewrite the line endings with the default line endings for this operating system, which print does by default. And that way, if my input file is from another operating system with different line endings, I'm actually serving to translate those line endings into the correct one for this operating system. So it's important to know that distinction. You may or may not want that, in which case you may choose to use the write lines method instead. Writing text files is simple in Python, and in the next lesson we'll talk about writing binary files. To copy a binary file, we use the read and write methods of the file object. Here in Komodo, I've opened a working copy of copybin.py from chapter 12 of the exercise files. And we have this input file, which is an image. This is a picture of a train station in Berlin, which I took on a trip overseas last year. I happen to love the train stations in Europe, and the whole train system in Europe is just so wonderful as compared to what we have here in the United States. And I thought this was a particularly beautiful train station. I took a number of pictures of it. And so we're going to use that for our data. And when I run this code, I'm just going to go ahead and run it so you can see it work. You notice I get my same progress bar here. Each bar represents 10 kbytes read and written. And my output file now here is berlincopy.jpg, and when I open that, you'll see that it's exactly the same picture. And so I've successfully copied a binary file. So you'll notice here on line 5, when we open the file, we're opening it with the B now for our file type, as opposed to T for text. If I try to open this in text and I try to run this, you notice I get an error. Unicode decode error. It's trying to read it as text, and the very first byte of the file is not a valid Unicode character. This has to be opened in binary mode, and when I run this, of course, it works. Likewise, our output file is open for write in binary, and then we have our while loop. You notice that I'm using as the condition for the while loop just the literal true, so this loop will run continually until I tell it to break. And I give it a break down here on line 12. The first thing we do in the loop is we read a buffer full. And you notice I'm using 10 kbytes as the size of the buffer. Now, you don't want to read the whole file at once because you don't necessarily know how big the file is, and you may not even know how much memory is available for your program. So you want to pick a buffer size that you know is going to be safe. Obviously, 10 kbytes is incredibly small for most modern desktop systems, but if perhaps you were in some other environment, some mobile environment, or some other small environment where memory is limited, this might be a reasonable size to read at a time. And so this is just the size of the chunks that you're reading and writing at a time. It's not a limit of how big the file can be. Rather, it's just a nice limit of how much memory you're going to use while copying the file one chunk at a time. Then we test if there is data in the buffer, and of course an empty buffer is going to have a false comparative value, and anything that's not empty is going to be true. And then we write the buffer. It's as simple as that, outfile.write with the buffer, and then we print our little dot, and if the buffer is empty, we call break. So it's as simple as that. And that breaks us out of the loop. We close the file. Again, we're closing the file to flush any buffers and make sure that the file is written properly. And we print a new line and done. And so when I run this, as you've seen, we get a perfectly good copy of our input file. Copying a binary file is a bit different from a text file, but it's still pretty simple. Choose your buffer size carefully, considering the target environment for your code. The Python standard library provides a rich set of built-in functions for working with numbers. Here in Komodo, I've opened a working copy of types.py from chapter 13 of the exercise files. And you notice here down on line 4, we're initializing x with a literal string with the digits 4 and 7 in them. And then I'm using the int function. And what's interesting about the int function is it's actually not a function, it's a constructor for the int type, and it'll return an int from another type. And so when I run this, you'll notice that we're printing out down here on line 7, we're printing the type of x and the value of x, and the type of y and the value of y. And we see that x is a string, and y is an int. And so we're converting a string to an int by calling the int function, which is actually the int constructor. Likewise, there's a float constructor, and when I run this, you'll notice that our result y is 47.0 because that's the standard way to represent a floating number with a decimal point, and it says class float. I can use the abs function to return the absolute value of a number, and so if I say minus 47 for x, we notice that it's still an integer, but we now get the absolute value, which is a positive 47. And this also works for floats. If I say minus 47.3, we get a 47.3 as the result, and it is also float. Now if I put this back to a integer number, and I'm going to use the function divmod, which will return both the quotient and the remainder in a tuple of a division. So if I say x and 3, it returns a tuple with two values of 15 and a 2. So we know that 15 times 3 is 45, and that leaves a remainder of 2. The complex function, again, is a type constructor. Complex numbers are two-dimensional numbers. Python uses j instead of I for the imaginary part of the number. Either one of them is standard in different disciplines. This is normal in engineering circles. So for example, if I say y equals x plus 73j, got too many y equals there, and we run this, you notice that the class is complex and the value is 47 plus 73j, so it has the imaginary part of the number in it. You can also create a complex number with the complex constructor, which looks like this. And when I run it, we get exactly the same result. Python has a complete set of numeric functions. The documentation has a complete reference here at docs.python.org/3/library/functions.html. The Python standard library provides a number of useful string-oriented functions beyond the methods of the string class itself. Here in Komodo, I've opened a working copy of hello.py from chapter 13 of the exercise files. And let's just go ahead and make this into a string. And I want to print the repr function of s. And when I run this, you notice that repr will print the string itself. So repr stands for representation. It'll print the best possible string representation of a value, or an object rather. What's interesting about this is if I create a class here, and let's say I initialize my variable with this, now when I print the representation of it, you'll notice it says it's a bunny object at, and it gives me the memory address. This is not terribly helpful. What representation does, what repr does, is it will print the value returned by the special repr method. And so if I say def repr, and I'll return a string. And now when I run this, the repr is going to have that string. The number of bunnies is 47. Now this is distinct from what happens if I just print S like this, and I'm going to change this to X because we're going to use a lot of different types here, not always strings. Now when I run it, you'll notice that it says exactly the same thing. So the repr function will either print the return from the repr method of the class, or if it doesn't have that, it'll print this. Let me just change this, put an X in front of it, and when I run it, you see it prints this main bunny object at. On the other hand, if there's a string method, this is the string representation, and I'm just going to put the word string in front of this, and this will be repr, so we can see which one is being preferred. Now, just the print function will take the string version, whereas the repr function will take the repr version. And so this allows you to customize how it's going to be represented in different contexts. So if you do have the string version, it'll default to the string version. If you don't have the string version, it will default to the repr version. And if you don't have either of them, it will print that representation. Now, if we have the ASCII function, works just like repr, and so when I run this, you see it uses the repr method, except it'll escape any special characters. So for example, if I put in a emoji of the live long and prosper hand, and I run this, you notice that it gives me this escaped value of the Unicode number. But if I use repr instead, it actually gives me the emoji. So that's the ASCII function, which will make sure that that representation is only ASCII characters. There's also a character function, and I'm going to give it a number here, which I happen to know because I have it written down, is the Unicode position for that live long and prosper hand. And you'll notice that the character function, and I'm just going to print that, you notice that the CHR function actually prints the character represented by that Unicode position. On the other hand, there's an ORD function, and I'm just going to copy and paste our little Unicode character. And when I run that, oops, I need to put it in quotes, don't I? And when we run that, you notice that we get that number. So ORD gives you the number of a character, and CHR gives you the character of a number. So Python provides a number of useful string-related functions. See python.org for a complete reference here at docs.python.org/3/library/functions.html. The Python standard library provides some useful functions for working with containers. So here in Komodo, I've opened a working copy of hello.py from chapter 13 of the exercise files. And I'm just going to start by declaring a tuple. And I'm going to assign y equals x and print both of them. And when I run this, you see we get two copies of the same tuple. Now I can say y equals len of x, len, that'll give me the length of x, and you see that y is now the number 5. I can say y equals reversed of x, and this will provide me with an iterator, so when I print it, we get this reversed object string. On the other hand, I can create a list out of that, and that will give me a reversed list of the tuple in x, or I could use reversed directly if I wanted to in a for. I could say for I in y, print I, and you see we get 5, 4, 3, 2, 1, the reversed list. There's a sum function. When I run that, you notice I get the number 15, which is the sum of 1, 2, 3, 4, and 5. I can give some a starting place, and so instead of 15, it'll give me 10 plus 15. When I run this, it's 25. There's also a max and min function, so max will give me the largest value in the collection, and min will give me the smallest value in the collection. And then we have a couple of interesting Boolean values that we can get from functions. Any will give me true if any of these are true. So if I replace this with all zeros and run it, then I get false. But if I make just one of them a 1, you'll notice that the result is true. There's also an all function, which will return true only if all of them are true. So obviously one of them is not enough, but if I make all of them true values, then I get true. There's an interesting zip function which works very differently. And so I'm going to declare y equals 6, 7, 8, 9, and 10. And I'm going to say z is zip of x and y. And then z returns an iterator, so I'm going to say for a and b. So z returns an iterator with 2 values in each item. In z, print a and b. And when I run this, you notice we get the zip of these two lists. So the first element is 1 and 6, the second element is 2 and 7, see the third is 3 and 8, 4 and 9, and how that works. So it's zipped them together, which can be useful in some circumstances. And then finally, there's enumerate. And for this, I'm just going to use an entirely different tuple here. I'm going to say cat, dog, rabbit, and say a velociraptor. Might have noticed that I enjoy some of these animals. For I, v. So enumerate gives us 2 values, an index and the value in enumerate of x, and we'll print I and v. And when I run this, you notice that I get an index and the value for each of these. I is a number starting with 0 and a value. So this can be useful in getting the order of things. For a complete reference of all collection functions, see the documentation here at docs.python.org/3/library/functions.html. The Python standard library includes functions for working on classes and objects. Here in Komodo, I've opened a working copy of hello.py from chapter 13 of the exercise files. And I'm going to start by defining a couple of variables. Here we have a literal integer and type of x. And we'll print x, and we'll print y. And when I run that, we get 42, and the type is int. So this is the type function, which operates on an object, and it returns the class of that object, or the type of that object. Class and type is pretty much the same thing in Python. Now, that doesn't help us a whole lot if we want to introspect inside of code, and if we want to ask, is this an instance of a particular class or not? And so for that, we have the is instance. And I can ask it if it's an instance of int, and if I run this, I'll get true. And if I make that 42.0, then I will get false, because that's an instance of float. And then finally, there's the ID of, so I can say ID of x, and that'll print this number that represents a unique number for that particular object. And so if you have the same object, the numbers will be the same. And if you have 2 different objects, the numbers will be different. For more details on these and other functions, please see the python.org documentation at docs.python.org/3/library/functions.html. The Python standard library includes a wide selection of modules available for your use in a standard Python installation. If we scroll down here, you see this is the whole library, so it also includes functions and classes and all kinds of things. But starting in section 6, these are all modules. And for example, here's the documentation for the sys module. And this is system-specific parameters and functions, and so you have many, many things you can do. So let's take a look at how this works. Here in Komodo, I've opened a working copy of modules.py from chapter 14 of the exercise files. And you notice the import statement, that's where I import a module, and then I use a module like this, just as any other object. I say sys dot, and version info is an element inside of the class of the module. And version info returns a collection of information, and so I can use it with an asterisk here, and it will give me a list of parameters. And in this case, the list of 3 for the major, minor, and minor parts of the Python version number. When I run this, it says Python version 3.6.3. Of course, your version may be different if you have a later version of Python. In any event, the system or sys module provides a number of things. For example, we can get platform. Now, this is the platform, not the operating system. And so when I run this, it says Darwin because I'm on a Mac, and that's what the Mac reports its platform as. If you're on a PC or something else, then you'll get a different string. On the other hand, if we import OS, we get operating system related functions, and I can say os.name. And when we run that, we get POSIX because a Mac runs Mac OS or OS X, which is an implementation of BSD Unix, which reports as POSIX because it's a standards compliant Unix variant. Of course, if you're on Windows or something else, you'll get a different string here. OS gives us a number of interesting and useful things. There's a function called getEnv, and I can get from the environment, I can get a particular variable, and in this case, I'm going to get the path, and when I run this, you see there's my path. Again, yours may be different. It probably is. I can get the current working directory, get cwd, and there's my current working directory. Again, yours will be different. Or I can get a random number. This is from the operating system random generator. And I'm going to get a random number 25 bytes long. And when I run this, you notice I get 25 bytes. So that's a byte object. If I want to, I can see that in hexadecimal using the hex method on the byte object. And when I run that, I get this nice hexadecimal number, which is cool and useful. And every time I run it, I get a different number. There is a whole random module which does more cool things with random numbers. I can say x equals list, or rather, we'll start with this. X equals random dot randint. So this will be giving a random integer between 1 and 1,000. And print x. And that's a random integer between 1 and 1,000. When I run it, every time I run it, I get a different number, and you should too. I can shuffle a list. So remember, a list is mutable, so I need a list, not a tuple. List of, give it a range, say 25 numbers. And when I print it, I get a list of 25 numbers, and I can say random.shuffle x, and then I print x again. And now it's shuffled, and every time I run it, I get a different shuffle. So that can certainly be useful. There's a date time module. We're just looking at a few of them here. Obviously, there are a lot more. There's a date time module, which can be very useful. Let's say now equals datetime dot datetime dot now. And if I print now, you see that I have this string representation, year, month, day, hour, minute, second, and microsecond. On the other hand, I can say now.year and just get the year part, now.month, day, hour, minute, and I can get each of these as a separate number, seconds and microseconds. And when I run this, you see those are all the separate numbers, year, month, day, etc. I strongly suggest you go through the documentation and find out what modules are available so that you can use them and not reinvent the wheel. Modules included in the standard library tend to be very well-written, feature-rich, and useful. Python makes it relatively easy to create your own reusable modules. Here in Komodo, I've opened a working copy of saytimetest.py from chapter 14 of the exercise files. This is an exercise that I tend to give myself every time I learn a new language. And of course, I learned Python a number of years ago, and so this module has been around for a while. But what this particular exercise is to write a class that will print the time in words. So when I run this, you notice on the last line here, there's a lot of unit tests before that. It says local time is 14 till 4. And so the exercise is for me to be able to write a module that will give me the time in words like that. And if we look up here at the unit test data, I've given it a number of times of day. 00 is midnight, 1 past midnight, 11 o'clock, noon, 1 o'clock, 29 past noon, half past noon, 29 till 1, quarter past noon. So there's all these different times in words, and this is the way that a person might look at their analog clock and they'll say it's 2:45. And then I have tests for boundaries. 160, that's out of range. 2400, that's out of range. Those aren't real times. And of course, in order to do this, I need to start with numbers. And so here's my numbers tests. 0, 1, 2, 3, 4, etc. 10, 12, 15. And so all of these, it has to be able to speak all of these numbers. It only goes up to 1,000. And so 1,000 is out of range, 999. I think my C language version, I went crazy and had it go into the billions, but this is my Python version. And so that's basically how this works. So this is the test script that imports the module. So I have import saytime, that imports the module. And then in my main here, I create an object and I print numbers test. And then here's a list of numbers that we test. And so for in the list, we print the number in words. And then we do the time test, and here's a list of tuples with hour and minute, and then we print those in words. And then we print the local time, setting the time to now. And so when I run it, of course, now it's 11 till 4 because I've been running my mouth for a few minutes. Now, if we come over here to the saytime module, we can take a quick tour through that. Again, I'm not going to go through all the details, but you have the module and you can certainly look at it and dissect it all you like. So first I have a class called numWords, which returns a number as words. So 42 becomes 42. And you see that I have that nice little doc string there. And then I have my data. So I am of the belief, and this has always worked for me, that if you design your data before you write your code is going to be a lot easier to write. And so in this case, I designed my data very carefully. And so you'll notice that my words list is a dictionary of tuples. So ones, and there's 0, 1, 2, 3, tens, 10, 20, 30, 40, teens, 10, 11, 12. And so by designing my data like this, it made my code very intuitive to write. And so I have words ones sub n, words teens sub n. So actually getting in there and finding the data, it becomes relatively simple. I then have a saytime class, which inherits from my numWords class, return the time from two parameters as words, And so I have specials, noon, and this is a dictionary, noon, midnight, till, and past. So it would be easy to internationalize this, to make it work in different languages, wouldn't it? And when it comes down here to the words, again, because the data is designed well, and I've inherited from the numbers class, that's not a lot of code to do what it is that we're talking about doing. And again, you can go through this code in detail because you'll have all of this code. And then I have a special class called sayTime_t, which inherits from sayTime, and all it does is it initializes itself with the current time, and then you can print the words. So you'll notice that this is a module, and at the bottom of the module, I have this if name equals main. So if I run the module, as I did before, then I can import it and I can use it and I can get all of this. But if I run the module directly, when I run it, I just get a till 4, because what main does is first it tests to see if we have any command line arguments. So when I run this from a command line, I can say saytime.py space test, and it'll run my unit tests. But if I don't do that, it just prints the current time in words right down here on line 141. So these are some useful techniques for creating your own modules. And this is a relatively simple process, especially once you understand the language, which hopefully if you've gone through the course and sequence, you now understand the language pretty well. As always, I suggest you write some code of your own to gain experience creating modules. The Python Database API provides a common interface for various database engines to the extent that it's possible to do so. Here in Komodo, I've opened a working copy of dbapi.py from chapter 15 of the exercise files. The Python DB API is a consolidated interface for a number of database systems. It's important to understand that every database engine has its own interface, its own requirements, and really its own paradigms, so no single interface will ever serve all of them equally. So understand the Python DB API will not be exactly the same for every database system. Like many scripting languages, Python ships with SQLite. SQLite is a fully functional, cross-platform database system that's suitable for many online and mobile applications. For more about SQLite, see my course, SQL Essential Training, and SQLite 3 with PHP Essential Training. If we look here in the main function, the first thing we do is we connect to the database, and that's done with the SQLite3.connect method. So the database API in this case, and in any case within Python, will be integrated into the module for the particular database engine that you're using. So in this case, we're using SQLite 3. You see on line 4, I import SQLite 3, and we call connect on the SQLite 3 object. And that'll return a database handle. And that database handle, in turn, we can use it to interface with the database. In this case, the first thing we do is we grab a cursor from the database handle. And this is a paradigm within the Python database API that will allow us to keep track of where we are in the database as we run database commands. And then on the database cursor, we print the create message. On the database cursor, we call execute to actually execute SQL. I'm just going to run through this here for you real quick. Our first SQL is to drop table if it exists, and then we create a table, and then again we print a message, we insert a row, and we use the SQL insert command, and we insert a couple more rows, and then we commit. If we want a count of the number of rows in the table, we use select count, and we fetch one from the cursor after we execute that SQL command. So that will return a row with one element in it that will have the count of the number of rows in the table. And then I can print that variable. There are count rows in the table. If we run a select statement that returns multiple rows, we can use a for statement and print each row. And then we can drop the table from the database and close the database. Now, the thing to understand about SQLite is that your database will be fully contained in one file, and this one file is completely portable. You can use the same file on Windows or on a Mac or on Unix or on whatever, and you'll be able to interface with any SQLite driver in any language and use that database, which is all in one file. So when I run this, it'll create a file. And again, if we go back up here to our Connect, you notice that we specify a file name here. And that file name is the file that'll be created. So when I run this, you'll notice over here in our file listing, we now have this dbapi.db file. And here's our rows: connect, create, insert row, insert row. There are 3 rows in the table, and then we read them, and there they are. And again, if we look at our insert statements here, those are the rows that we inserted. So this is just a quick overview of how this works. The Python DB API interface is fine for casual use. If you need to do anything more significant, you'll want to create a class or a module with more robust interface, and I'll show you an example of that in the next lesson. For many purposes, the Python DB API is all you'll need. If you're doing a significant amount of database coding, you'll want something more robust. Here in Komodo, I've opened a working copy of bwdb.py from chapter 15 of the exercise files. This is a database interface that I've created and used over many years and in several different languages. It's not exhaustive, but it provides sufficient functionality for most uses, and it's extensible. This interface uses SQLite, which I use a lot. I find it both powerful and convenient, and in many cases, a more reliable and robust choice than a client-server system like MySQL. So let's take a look at this interface. Down here on line 8, I import SQLite 3, and here's my constructor. And you'll notice that in each of my functions, I have what's called a doc string. This is a Python paradigm, I may have mentioned it before, where if you put a string as the first line, just a bare literal string as the first line of any function, method, or class, that serves as documentation for that function, method, or class. It's traditional to use the triple quoted strings like this, and so that's what I've done. So this is the constructor, and this docstring talks about how to call the constructor, and it describes it so that I'll always know how to use this when I come back to it years later, perhaps after not using it for a while. The file name uses property decorators, and this is something I haven't talked about because in actuality, I find them rather counterintuitive, and they're a little bit useful because properties are a useful thing, but I don't really care for the implementation too much. But I left it in here because originally it was an experiment, and I left it in because it's good to show you how it works. So you'll notice way down here towards the bottom of my class, I have methods for dealing with the file name property, and these methods use the property decorator and setter and deleter decorators. And so the first one is just the getter. It's for reading the file name, and it simply returns the file name. The setter is for assigning a value to the file name, and when I assign a value to the file name, I actually do a fresh connect to the database, and I set up the row factory, which we'll talk about a little bit later. And then the file name deleter, I actually just close the database. And so this can be considered useful because all of this happens just by setting or reading the file name property. In practice, it's not fully implemented. The deleter doesn't always get called under all circumstances, and it's a bit of a mess. And this is one of the areas where Python still needs to do some work, and I expect that they will in a future version. But for right now, that's how it works, and I left it in here so I could demonstrate it. Then I set the table, and the table is used for the CRUD methods, and we'll talk about that a little bit later. First, I'm just going to show you the SQL methods. And so I have SQL do, which is for non-select queries, queries that do not return any values. And you see it's just very simple. You pass it SQL, you pass it parameters, it passes those directly to the DB API. And then we have do with no commit. You'll notice I have a commit after that do, and I have no commit after this one. In many database languages, commits are required, and some they're not. And in any case, the whole point of commits is to be able to do several database commands and then commit them all at once so that it creates efficiency and you can reduce the number of disk I/O operations. And so I have both with commit and without commit for all of my write operations. SQL query, it passes an SQL statement to execute, and then it returns a generator so that you can use this with a for loop. And I use yield here for this. You can query a single row and it calls fetch one, or you can query a single value and it returns just the first column from the first row. And then there's a commit statement, and now we have the CRUD section. So CRUD is C-R-U-D, and it stands for create, read, update, delete. It's the basic 4 functions of any database system. And this is one of the most useful things I feel about having this library is that I have these CRUD methods, and you'll see in my unit tests down below how convenient these are to use. And so I have a record, a single record, get multiple records with a yield that returns a generator. I have an insert without commit, and here I take this record. These are all record-based, so you pass these a dictionary, and they return dictionaries, and these dictionaries have all of the column names in the keys. And so I pass a dictionary to this insert, and it introspects the dictionary, gets all of the keys, builds the SQL query. And again, this is relatively simple in Python, and then it executes it. And it returns the inserted row ID, and the SQL is called last row ID. Or rather, in the SQLite database driver, it's called last row ID. And then I have a version of it with a commit. So that was the no commit version above. And so this is the with commit version. It simply calls the no commit version, and then it does a commit and returns the last row ID. And just like insert, I have an update that also is dictionary based, and it builds our SQL based on the properties of the dictionary, and it calls execute, and then I have the version down below here with commit. And then I have a delete, and likewise, it builds the SQL and executes the delete, and then I have the version with commit. I have countRex, which does a select count and returns one value, and then I have these properties and close. So that's really it. It's a relatively simple database interface, and here's our test so you can see how this is typically implemented. I have a list of dictionaries for the records. Oh, you'll notice here that my file name, this is specific to SQLite. The file name is this special string, the word memory surrounded by colons, and this creates an in-memory database so we don't actually have to create a file. And this is great for testing stuff. If you want to do a file-based one, then you need to uncomment this stuff so that it can create the file and remove the file. So we print out the version, we create the database, and this is done by constructing the DB object, the BWDB object, and then we have do for creating the table. That's SQL do. And we use SQL insert to insert records into the table. And again, here I'm just looping over our list of dictionary entries and calling insert. Very convenient. I don't have to write any SQL for that. I count the number of records in the table with countRex. I read from the table again with a for loop, getRex, it returns a generator. So this is really easy. And I can update the table. I can change the value of one of the rows in the table. I can insert an extra row using DB insert and a dictionary entry. Again, this is all just really straightforward. And I can then delete the new entry, and I can retrieve the records either using the CRUD method or the SQL query method. And now I'm going to run this. I'm going to show you a couple of interesting things about this. I'm going to go ahead and bring this up so we see a lot more of it. There we go. I don't think that's everything. Is that everything? Yeah, that's everything. So we print out the version, we create the database file in memory, create the table, insert 3 rows into the table. There's now 3 rows. Then we read from the table, and the entries look like this. Update the table, changing 2 to a capital 2, capital T, W-O. Insert an extra row, delete the row. There's now 4 rows. Now we delete it. Now there's 3 rows. And then we print out the rows. You notice I printed it out in 2 different ways, and I want to show you about this. You recall that when I construct the database up here, I set the row factory to the built-in row factory. It allows you to read the rows in several different ways. It adds one small layer of complexity. I actually have to tell it what type I want for those rows. And so you notice that I use dict here, I use dict there to tell it that I want a dictionary back. In this case, I'm just giving you the basic row so that you can see this. And so we get these row objects down here. If instead I tell it I want it to be a dictionary, then we'll get dictionary entries. I'm going to run it here, and you see we get dictionary entries. Or if I tell it, say that I want tuple, then I run it and I get tuples or lists. And this is because it's a factory and it's not an actual dictionary row that it's being returned. And sometimes I'm going to want it in different types, and so that's why I decided to do it this way. So I know this is a lot to absorb, and please, go back over this, take your time, read it, feel free to email me with questions. But I wanted to show you this, and then in our next lesson, I'm going to show you a practical application where I actually use this. So I find this sort of database wrapper very useful. And like I said, I've implemented it in most of the languages that I use on a daily basis, including Python and C++. And so that I can write code based on these libraries, and it all makes sense to me. And as time goes on, I'll refine them as I did when I started this class. So as I said, in the next lesson, I'll show you a practical application where I've used this module. This is an example from my own toolbox. This is a short URL application that I use for my own website. For example, if I open a new tab here and I type in j.bw.org, which is my short URL server, and just LDC, this will take me to a particular page in my site, which I use for my lynda.com landing page. And so here I've got a copy of this database system running on a local server on this demo machine. So this is not the one that's running on my live server, so we can play with it a little bit. This page here is the back-end database of the system. From this web page, I can add, edit, test, and delete URLs. This code runs on a web server, so we won't be testing it in Komodo. This is running on a local server here on this Mac that I'm recording on. And it's important to understand that there's a lot of moving pieces for any web application. To implement this, it takes some knowledge of the web server. In this case, it's an Apache web server. It takes knowledge of, obviously, the language that you're writing scripts in this case, Python, also your database system. In this case, I'm using SQL, and some knowledge of HTML and CSS. And so there's a whole lot of moving pieces here, and they all have to work together in order to make this work. And so, for example, if I want to add a new entry here, I can put in the home page of my website, and I can put in a short token. For example, I want BW in this case. And when I click Add Record, it's now added that to the database. And we can edit that, we can bring it up, we can change that if we want to. We cannot change the short URL because that's used as a key. And if we want to, we can delete a record. So I can delete this one if I want to and confirm delete. I can also test them. You'll notice when I hover my cursor over this, I don't know how well you can see it on your screen, but down at the bottom there it says localhost/JURL/LDC. And so when I click on that, it redirects to the appropriate website. And this is using an HTTP redirect. And again, that's another moving piece, some understanding for this application of the HTTP protocol. So like I said, there's a lot of moving pieces and there are a lot of parts to this. We're just going to go over it really quickly in the time that we have allotted for this lesson. I'm going to switch now to Komodo Edit. And the first thing we're going to look at here is my working copy of JURL.py. And so all of these files are in the JURL subdirectory under chapter 15. And this is the entire system. This is everything that you need to run this on your web server, with the exception of, however, you need to configure your web server in order to be able to run Python scripts and whatever configuration you need to be able to run the types of redirects we're doing. So in this case, for Apache, and I've included this file, although this is almost certainly not exactly what you need even in your Apache server. So you won't be able to just drop this in and have it work. Unfortunately, configuring a web server is a very individual thing, and every web server is configured differently. So this almost certainly will not work when it's directly dropped in there, but it gives you an idea of what's needed to make this work on this Mac. This is not even the one from my web server. This is the one for this local testing environment. And the important thing to see here is the rewrite engine, which allows me to rewrite the URLs. And that allows me to use something like this URL that you see here, where it just says localhost JURL and the token. And this rewrite gets that passed as a proper CGI query. And so, like I said, there's a lot of moving pieces here to make this work, but the script itself is fairly simple. This is the redirect script, and you notice it's just 60 lines of code. And that's with spaces and comments and everything. It's probably less than 50 lines of actual script. A number of libraries involved here, and I've given you copies of all these libraries. These are all libraries that I've written myself, modules that I've written myself, one to handle CGI, the database one that we've already talked about, and one for operating with configuration files. I want to take just a moment and talk about why I write these separate modules, because there are publicly available modules to do what these modules do, and you can certainly use them if you like. In my view, many of the publicly available modules have features that I don't use that increase the complexity and reduce the efficiency of the code. I prefer simple and functional, and I don't mind creating them myself. In fact, I enjoy the process. I do this because I enjoy it, and I usually learn from the process. So I strongly recommend that you write your own modules for many of these tasks. You and your code will benefit from the exercise. So I've got one here for CGI, and that's the interface with the CGI protocol, which you need for most web applications. Of course, the database one you've seen already, and the one for working with configuration files. This is a technique that I often use in many languages, and I find this very useful. I'll create a global, in this case, a dictionary structure, but some sort of a global structure. Most languages have some sort of a hashed key value structure that works well for this. In Python, it's dictionaries. And this allows me to create some global variables without stomping on the global namespace. And I'll usually name it G. It's just a way that I've learned over the years that this works very well. Also, it's easily portable when I take a script and I rewrite it in another language. So the first thing that we do here for main is we call init. And so I'm going to scroll down here and show you init. Init sets up basically our global variables, sets up the CGI environment, reads the configuration file, and initializes the database. So that's all very straightforward. Here in main, we're reading various path variables and system arguments. We're basically setting up our environment, reading however it is that the information is getting passed to the script. And I make it possible to do it in a number of different ways. And then the real meat of it starts down here on line 40, where we'll look up a short URL in the database. And again, I'm using my SQL query value. This particular script doesn't use a lot of SQL, so I find it really simple to just type the query there. And you'll notice that I'm using the exception system for handling possible errors. Down here on line 46, this is where the redirect happens, and basically sending a status 302, which is an HTTP status, for a redirect along with the location. And that is it. This is a very simple script. The rest is just error checking and processing. This is a very, very simple script. This does the actual redirect. The more work is done in the backend system. db.py, this is the script that we saw here in Chrome. This has a lot more moving parts. This is the database management interface. And again, I'm using a lot of my own modules. HashLib is one that comes with Python, but there's my CGI module, my DB module, and one for template processing. to make the HTML easier. So you'll notice there's an HTML directory here, and there's a bunch of these little HTML files. I'll open one, and these have these variables in them, and this is my own templating system. Again, there's a templating system that comes with Python, and you're welcome to use it. I just find it large and cumbersome, and writing my own was an interesting exercise, and I like using it. It's written the way that I like to use it. So if we come back here to DB, you see I have again my global variable, and I find that very convenient. There's an init. I try to do things in the same way, so I'll always have a main and an init function, and this just helps me to be able to navigate my own scripts if I come back to something years later. And I've been using these techniques for many years, so I find this very convenient. So we set up the CGI, we send a header, we do all of these things to set up the environment for the script. Now, this dispatch function, this is an interesting bit of work. This is where a lot of the work of the script happens. So when you're navigating from one web page to another web page, because HTTP is stateless, it's really difficult to kind of keep track of where you are. So I deposit little breadcrumbs in the pages in the form of hidden CGI variables. These are variables using the hidden attribute. They exist in the CGI domain, and yet they're not visible on the page. And so I use those little breadcrumbs to navigate around, and every time the script enters, it has no state, but it gathers its state from those breadcrumbs, and then this dispatch serves as a jump table to tell it which page to display. Down here we have listrex. This is the code that does this on the screen, which will list the records. And you notice there's little arrows. We don't have enough records in here, but if there's more than a certain number of records, it will page. It'll put them on separate pages to make it easy to navigate. And so all of that is done in here. And beginning on line 177, we have our database navigation actions. We have one for adding records. We have one for editing records, deleting, confirming deletes, updates, and all of this uses my database interface, which makes the database part of this really easy and allows me to focus on the logistics of the actual code. The rest of the code in this file is about managing the templates and the HTML. I know this has been a lot, and I hope this helps you to see how simple and powerful Python can be in this sort of environment. Of course, there are a lot of other moving parts. There's the HTML, the CSS, managing the web server, understanding the database. There are all of these other parts, and with a little knowledge about these parts, Python allows you to create simple and powerful database applications. In this course, my goal was to provide you with the basic knowledge you'll need to write good, effective Python scripts. I've shown you the anatomy and basic syntax of a typical Python script so you can be well prepared to construct your own scripts. How types and values work with Python's rich object system. How to construct conditionals and loops. How to use functions, generators, and decorators. And we've covered Python's rich object model so you can create good reusable code and even leverage the code of others. I hope you've enjoyed this course as much as I've enjoyed creating it for you, so have fun and create something wonderful with your own Python scripts.